Welcome, gentle friend, to this quiet space we've created, a soft haven where the mind can wander freely, untethered by the demands of the day. Take a slow, peaceful breath now. Feel the gentle rise and fall of your chest, the subtle rhythm of your own being. In this moment, there's nothing to do, nowhere to be, except here, with these quiet words. As we begin a journey not just across distances, but into the very heart of wonder itself. This isn't about learning facts or solving problems. It's about allowing your mind to drift, like a feather on a soft breeze, through the boundless, mysterious tapestry of our universe. Imagine for a moment a profound question. Where are you right now? Perhaps you're nestled in a soft chair, or lying comfortably in your bed. Maybe it's morning, with the gentle light of dawn peeking through your window. Or perhaps it's the deep quiet of night, with shadows dancing softly in the corners of your room. Your precise location, your exact time, feels so real, so immediate, and yet this tiny bubble of now and here is just a single, fleeting point in an unimaginably vast ocean of space and time. To truly appreciate where we are, and how far we've come in understanding it, let us gently cast our minds back, far into the quiet mists of history. For countless generations, humanity's understanding of our place in the cosmos was like gazing into a dense fog. The world was flat, or so many believed, a finite plane beneath a dome of stars. The sun, moon, and planets were simply lights, moving across this celestial sphere, seemingly revolving around us. The unquestioned center of everything, our perception was limited by what our eyes could see, by what our feet could travel, by what our immediate senses could gather. The clouds of mystery, then, were not just metaphorical. They were the very limits of our perception, the edges of our known world. Consider the gentle, persistent efforts of early cartographers, those quiet, meticulous souls who first tried to map our home world. Imagine the old atlases, heavy with the scent of aged paper, their pages filled with intricate drawings of continents slowly taking shape. Edward Quinn's historical atlas, for instance, a beautiful artifact from the past, sought to capture the world as it was understood in different eras. On its yellowed pages, you might see terra incognita, unknown land, marked across vast, unexplored regions. These were the clouds of geographic ignorance, the blank spaces on the map where imagination filled the void that knowledge could not yet touch. But what drove these early explorers, these quiet, determined individuals, to push past the known, to venture into the unknown? It was a gentle, unwavering curiosity, a deep human yearning to understand what lay beyond the horizon. They risked their lives, sailing into uncharted waters, climbing unseen peaks, driven by the simple, profound desire to see what was truly there. And with each voyage, with each new discovery, a tiny corner of the cloud began to thin, revealing a little more of the Earth's true shape and vastness. The world, they slowly realized, was not flat, but a magnificent sphere, floating in an even grander, more mysterious void. This very same quiet, persistent curiosity, this unyielding desire to lift the veil of ignorance, extended far beyond our terrestrial home, reaching out into the velvet blackness of the night sky. For millennia, the stars remained distant, untouchable pinpricks of light, their nature a complete enigma. People wove stories around them, constellations that mirrored their hopes and fears. But their true essence, their vast distances, their fiery hearts, all remained hidden behind the thickest of cosmic clouds. Then, a gentle revolution began, not with thunderous pronouncements, but with the quiet, focused gaze of brilliant minds. Imagine Galileo Galilei, a man of profound insight, carefully grinding lenses, polishing glass, assembling the very first telescope to point towards the heavens. This simple, yet revolutionary instrument was nothing short of a cosmic key, gently unlocking doors that had been closed to humanity since the dawn of time. When Galileo turned his crude telescope to the moon, he didn't see a perfect, smooth sphere, but a world of mountains and valleys, craters and plains, much like Earth itself. It was a profound revelation, a quiet whisper that celestial bodies were not ethereal perfection, but physical places, real worlds. And when he pointed it at Jupiter, he saw tiny points of light orbiting the giant planet, not Earth. This was a direct, irrefutable challenge to the long-held geocentric view, the belief that Earth was the absolute center of all creation. It was a gentle yet powerful shift in perspective, moving humanity from the cosmic center to a quieter, more humble, yet infinitely more interesting place. This was just the beginning. With each passing century, telescopes grew larger, more powerful, their mirrors meticulously crafted, their lenses ground with increasing precision. From the early optical instruments that gathered visible light, we slowly, painstakingly, developed new ways of seeing the universe. Radio telescopes, like vast, silent ears, began to listen to the faint whispers of cosmic static, revealing hidden galaxies and ancient processes invisible to the human eye. X-ray telescopes, orbiting above Earth's obscuring atmosphere, unveiled the high-energy fireworks of black holes and supernova remnants. Each new type of telescope, each new way of collecting light, gently peeled back another layer of the cosmic clouds. What these instruments revealed was a universe far grander, far more dynamic, and far more awe-inspiring than anyone could have ever conceived. We learned that the stars were not mere points of light, but colossal, fiery suns, some even larger and brighter than our own. We discovered that our sun itself was just one of hundreds of billions of stars, all swirling together in a vast, disc-shaped collection called the Milky Way galaxy. And then came the truly mind-bending realization the Milky Way was not the entire universe. It was just one galaxy among billions, perhaps even trillions, each a sprawling island of stars, gas and dust, separated by unimaginable gulfs of empty space, the clouds of mystery, which once seemed to surround our tiny planet, now seemed to disperse, revealing an almost infinite cosmic ocean. But even as these clouds thinned, new, more profound questions began to emerge from the deeper darkness. If the universe was so vast, so full of galaxies, what was its history? How did it all begin? This question led to one of the most remarkable and gently unsettling discoveries of the 20th century. The universe is not static and unchanging. It is expanding. This profound realization began with the meticulous observations of astronomers like Edwin Hubble. He noticed that light from distant galaxies was consistently redshifted, meaning its wavelengths were stretched, much like the sound of a siren dropping in pitch as it moves away from you. The farther away a galaxy was, the greater its redshift, implying it was moving away from us faster. This wasn't just individual galaxies moving through space. It was space itself stretching, carrying the galaxies along with it. Like raisins in a rising loaf of bread, this expanding universe, when wound backward in time, pointed to a single, profound origin, a moment of immense density and heat. A cosmic genesis known as the Big Bang. Imagine, if you will, the entire observable universe compressed into an unimaginably tiny, infinitely hot point. A cosmic egg from which everything we know, everything we see, everything we are, gently bloomed into existence. It's a concept that can feel overwhelming, almost too vast to comprehend. But allow your mind to simply float with the image, not striving to grasp its every detail, but letting its profound implications wash over you. The Big Bang Theory, for all its power, was initially just that, a theory, a brilliant idea. But then came the quiet, Undeniable proof, the ultimate cosmic echo. In 1964, two gentle radio astronomers, Arno Penzias and Robert Wilson, while trying to eliminate persistent static from their antenna, stumbled upon something extraordinary, a faint, uniform glow of microwave radiation coming from every direction in the sky. This wasn't local interference, it was the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. It was the universe's oldest light, a relic from a time when the universe was only about 380,000 years old. Too hot for light to travel freely. Still a dense, glowing fog as the universe expanded and cooled. This light was finally able to stream freely, reaching us today as a uniform. Cool whisper from the dawn of time, this discovery was like finding a fossilized footprint of creation, a tangible link to the very beginning. The cosmic clouds, once thick and impenetrable, had parted further, revealing the universe's fiery birth and its ongoing, majestic expansion. We had moved from a geocentric view to a heliocentric view, then to a galactocentric view, and finally, to a truly cosmic perspective, understanding our place within a dynamic, evolving, unimaginably ancient universe. Yet, even with these profound discoveries, new clouds of mystery have formed on the horizon, perhaps even deeper and more perplexing than those we've already navigated. The universe, we now realize, is filled with things we cannot see, cannot directly touch, cannot fully comprehend. The visible matter, the stars, planets, galaxies, everything we interact with makes up only about 5% of the total mass and energy of the universe. The rest is comprised of two elusive, silent entities, dark matter and dark energy. Imagine trying to understand a symphony by only hearing 5% of the notes. That's a little like our current situation. Dark matter, making up about 27% of the universe, is a mysterious substance that does not emit, absorb, or reflect light. We cannot see it directly. Its presence is inferred only by its gravitational effects on visible matter. Galaxies spin too fast to hold together with just the visible matter we observe. There must be an unseen gravitational glue, a vast, invisible halo of dark matter holding them intact. Galaxy clusters are far more massive than their visible stars suggest, their powerful gravity bending light from background galaxies through gravitational lensing. Another silent clue to dark matter's pervasive influence. The very structure of the cosmic web, the vast filaments and voids of galaxies, seems to be shaped by this invisible scaffolding. It's like feeling a powerful, unseen current in the ocean, knowing it's there only by the way it pulls on the boats, even if the water itself appears still. And then there is dark energy, even more enigmatic, making up about 68% of the universe. It is a mysterious force that appears to be causing the universe's expansion to accelerate, instead of gravity slowing things down. As one might expect after a Big Bang, the universe is speeding up, pushing galaxies further apart at an ever-increasing rate. This is perhaps the deepest, quietest puzzle in modern cosmology. What is this dark energy? Is it an intrinsic property of space itself? A subtle, repulsive pressure woven into the fabric of reality? Or is it something else entirely? A new field? A cosmic constant that we are only beginning to glimpse, we do not know for certain. And the cloud of dark energy remains dense and alluring. So, even as we celebrate the dispersal of old clouds, the unveiling of our cosmic address, from a flat Earth to a tiny planet orbiting an ordinary star in a vast galaxy within an expanding universe born from a Big Bang, new, profound enigmas emerge. The universe, it seems, is far from fully revealed. It continues to hold secrets, to whisper questions, to invite us into deeper states of contemplation. As our first chapter gently concludes, allow your mind to float with these grand, humbling ideas. Ponder the immense scale of what we know, and the even greater scale of what we don't. Feel the quiet wonder of existing in a cosmos so vast, so ancient, so full of seen and unseen mysteries. There is a deep peace in this boundless curiosity, in letting go of the need for definitive answers and simply embracing the infinite possibilities. Let these thoughts gently prepare your mind for a state of deep tranquility, a peaceful drifting towards inner quiet. Welcome back, gentle friend, to our quiet journey through the universe's grand narrative. Take another soft breath, allowing the vastness we've just contemplated, the hidden dark matter, the mysterious dark energy, to settle peacefully within your mind. We often think of these cosmic unknowns as simply empty space or unseen forces. But perhaps they are merely subtle whispers, gentle invitations to expand our understanding even further. Today, we will softly explore an idea that pushes the boundaries of imagination, one that suggests our universe, in all its wondrous complexity, might not be the only one. We will drift into the concept of the multiverse, a tapestry of realities far grander than a single cosmos. Imagine a single grain of sand on an immense, infinite beach. Our universe, with all its billions of galaxies, its unfathomable distances, its intricate laws of physics, could be just that single grain of sand. The beach, then, would be the multiverse, an almost incomprehensible collection of other universes, each perhaps subtly or profoundly different from our own. This idea, once relegated to the realms of pure philosophy or science fiction, has now emerged as a serious, albeit still speculative, area of inquiry in modern cosmology. It is a concept that offers a gentle answer to some of the universe's deepest puzzles, and a quiet sense of awe at the boundless possibilities of existence. One of the most compelling reasons to even consider the multiverse comes from what we call the fine-tuning of our own universe. As we gently explored in our previous chapter, our universe sprang into existence with the Big Bang. And since then, its laws and fundamental constants seem to be set with an astonishing precision, almost as if they were delicately adjusted to allow for the emergence of stars, galaxies, and eventually, life. Consider, for a moment, the strength of the fundamental forces. If the strong nuclear force, which binds protons and neutrons together within atomic nuclei, were even slightly weaker, atomic nuclei wouldn't be stable, and no elements beyond hydrogen would form. No carbon, no oxygen, no iron, no building blocks for planets or life. If it were slightly stronger, hydrogen would have fused into helium too rapidly in the early universe, leaving insufficient hydrogen to fuel stars, and leading to a universe of heavy, inert elements. Similarly, the electromagnetic force, which governs the interactions between charged particles and gives rise to light. Electricity and chemistry is finely balanced. If it were a tiny bit weaker, electrons wouldn't be held in orbit around atomic nuclei, preventing the formation of stable atoms and molecules. If it were slightly stronger, electrons would be pulled too tightly, making chemical reactions the very basis of life impossible. Even the masses of fundamental particles, like electrons and quarks, seem to be perfectly set. If the electron were much heavier, stars would burn out too quickly, and complex chemistry might not occur. If quarks were different, the very existence of protons and neutrons might be unstable, preventing the formation of any matter as we know it. And then there's the cosmological constant, a term in Einstein's equations that describes the energy density of empty space. Often associated with dark energy, our universe's cosmological constant is incredibly small, but not zero. If it were much larger, the universe would have expanded so rapidly in its early moments that matter would have been diluted to an extreme degree, never coalescing into stars and galaxies. If it were negative, the universe would have quickly collapsed back in on itself. Long before life could emerge, its value is so exquisitely precise, so perfectly balanced, that it seems almost too good to be true. This astonishing fine-tuning presents a profound question. Why are these values precisely what they are? Why is our universe so perfectly suited for the emergence of complexity? For stars, for planets, and for consciousness to wonder about it all? One possible answer, a gentle whisper from the depths of cosmic possibility, is that our universe is simply a fluke, an incredibly improbable roll of cosmic dice. But for many scientists, this explanation feels unsatisfying, almost like saying it just happened, without truly grappling with the profound improbability. This is where the idea of the multiverse offers an elegant, if mind-bending, alternative. If there are indeed countless other universes out there, each with different fundamental laws and constants, then it is no longer surprising that at least one of them, our own, happens to have the exact right conditions for life to exist. It's like a vast cosmic lottery if you buy enough tickets. Eventually, one of them is bound to win. Our universe is simply the winning ticket, the one where the conditions were just right for us to exist and to marvel at its wonder. Max Tegmark, a brilliant cosmologist, has gently categorized different types of multiverses into what he calls levels, helping us navigate this profound concept. Let us quietly begin with Level 1, the infinite universe. Imagine our own observable universe, the sphere of space from which light has had enough time to reach us since the Big Bang. This sphere extends roughly 46.5 billion light-years in every direction from us. But what lies beyond that boundary of space is truly infinite, as many cosmological models suggest. Then it simply continues forever. And if it continues forever, then due to the finite number of ways that matter and energy can arrange themselves, eventually, everything must repeat. Think of it like shuffling a deck of cards. There are a finite number of arrangements for a deck of 52 cards, if you shuffle it enough times. You will eventually repeat a previous arrangement. Now imagine the universe not as a deck of cards, but as an unimaginably vast, perhaps infinite, set of quantum particles, arranged in a specific configuration. If space truly extends infinitely, and if the possible configurations of particles within a given volume are finite, albeit astronomically huge, then statistical mechanics tells us that identical configurations must eventually repeat. This means that somewhere, far beyond our observable horizon, perhaps unimaginably far away, there is another galaxy identical to our Milky Way, and within that galaxy, there is another star system exactly like our solar system, and on one of those planets, there is another Earth, and on that Earth, there is another you. Perhaps living out this very moment, reading these very words, experiencing the same quiet sense of wonder. And not just one copy, but infinitely many copies. Living out every possible variation of your life. Every choice made and not made. It's a subtle, almost eerie thought, suggesting that every possible version of your existence is being lived out somewhere. At this very moment, across the boundless expanse of an infinite space, this Level 1 multiverse doesn't require new physics beyond what we already know. It simply takes the idea of an infinite universe to its logical, gentle conclusion. It's a universe of infinite copies, where every possible cosmic history, every possible arrangement of matter, is realized somewhere. It's a universe of profound repetition, where every unique event eventually finds its echo in another distant corner of the cosmos. This realization can bring a quiet sense of liberation if every possibility is explored somewhere. Then perhaps there is no true right or wrong path, only different journeys in a boundless landscape. Now, let us gently ascend to Level 2. Other bubble universes with different physical laws. This level is far more speculative, but it addresses the fine-tuning problem even more directly. It arises from a powerful and elegant extension of the Big Bang theory called eternal inflation. Imagine, for a moment, the very early universe, just moments after the Big Bang, instead of a single. Uniform expansion. The theory of cosmic inflation posits a period of incredibly rapid, exponential expansion, far faster than the expansion we observe today. During this brief, mind-bending epoch, the universe swelled from something smaller than an atom to astronomical scales in a mere fraction of a second, smoothing out irregularities and creating the vast, flat universe we see today. But what if this inflationary process, once it started, never truly stopped everywhere? This is the core idea of eternal inflation. Imagine the universe as a vast, frothing ocean of inflating spacetime. In some regions, the inflation might gently slow down and stop, forming a bubble or a pocket universe, a distinct region of spacetime where the expansion has settled. Allowing matter and structure to form, our own observable universe would be just one such bubble, a calm pool within the turbulent, eternally inflating ocean. But in other regions of this vast, inflating ocean, the inflation might continue, ceaselessly stretching space. And within this endlessly inflating background, new bubbles, new pocket universes, would constantly be nucleating, perpetually popping into existence like new air bubbles forming in boiling water. This process would be eternal, forever creating new universes. Here's the profound twist for level 2, because these bubble universes are born from a chaotic quantum process. The precise laws of physics that crystallize within each new bubble might be different. Think of it like water freezing. When water freezes into ice, it forms crystals, but depending on the conditions, temperature, pressure, impurities, the crystals might form with slightly different structures. In a similar way, as a new bubble universe cools and inflation ends within it, the fundamental physical constants, the masses of particles, the strengths of forces, and even the number of spatial dimensions that unfold, could take on different values. So, in one bubble universe, gravity might be much stronger, causing stars to burn out almost instantly. In another, electrons might be much heavier, preventing the formation of stable atoms. In yet another, there might be 5 large spatial dimensions instead of our familiar 3, leading to an entirely different kind of cosmic structure. And in one very special bubble, our own, the physical laws happen to be just right, exquisitely tuned to allow for the emergence of complex chemistry, long-lived stars, and the conditions necessary for life to evolve and flourish. This level 2 multiverse elegantly solves the fine-tuning problem. It's not that our universe is a fluke, it's simply that in an infinite ensemble of universes, every possible combination of physical laws is realized somewhere. We exist in the universe where the laws allow for our existence. It's a powerful and liberating idea, suggesting that the universe is not just vast in space, but boundless in its very nature, capable of supporting an unimaginable diversity of realities. These other bubble universes, spawned by eternal inflation, would be fundamentally inaccessible to us. They would be inflating away from us at speeds far greater than light, forever beyond our cosmic horizon. We could never travel to them, never observe them directly. They exist in a realm of profound separation, connected only by the shared, eternally inflating superspace from which they all emerge. This concept, the level 2 multiverse arising from eternal inflation, is currently one of the most widely discussed and researched ideas in theoretical cosmology. It bridges quantum mechanics, which governs the tiny fluctuations that seed these bubbles, with general relativity, which describes the large-scale expansion of spacetime. It's a gentle yet profound marriage of the infinitely small and the infinitely large, hinting at a universe that is far more abundant and diverse than our single, observable cosmos. As you gently drift through these concepts, allow yourself to simply imagine these possibilities. There is no need to grasp every detail, no pressure to fully comprehend the mathematical intricacies. Just feel the quiet sense of expansion, the boundless nature of reality that these ideas evoke. Perhaps in this gentle contemplation, you might find a deeper peace, a quiet understanding that our universe, while incredibly special to us, is but one note in an infinite cosmic symphony. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet unfolding of cosmic possibilities. Take another soft breath now, allowing the immense scale of the Level 1 and Level 2 multiverses to softly expand in your mind. We've imagined infinite copies of ourselves in countless bubble universes, each with its own unique set of physical laws. Today, we will gently explore even more profound and poetic ideas about how a multiverse might come into being, drifting into concepts that are still at the very edge of human understanding, but which offer a deep sense of wonder about the universe's boundless creativity. Imagine, if you will, that the birth of a universe isn't a singular, isolated event, but part of a grander, cyclical dance. This brings us to the fascinating and often gently reassuring idea of cyclical universes, sometimes called oscillating or bouncing universes, instead of a single Big Bang followed by endless expansion. What if the cosmos goes through an eternal cycle of birth, death, and rebirth in this quiet vision? Our Big Bang wasn't the absolute beginning, but merely a new chapter, a cosmic rebound from a previous universe's end. Imagine the universe expanding, much as ours is now, reaching a maximum size. And then, perhaps under the influence of gravity pulling everything back together, it begins to contract. This contraction would continue, gently at first, then accelerating, until all matter and energy are compressed back into an incredibly dense, hot state. Much like the one before our Big Bang, this moment of maximum compression is sometimes called the Big Crunch. But instead of ending in a singularity, this Big Crunch, at its very peak, might somehow bounce back, leading to a new Big Bang and a fresh period of expansion. It's like a cosmic heartbeat, eternally contracting and expanding, a perpetual cycle of death and rebirth for the entire cosmos. Each bounce would give rise to a new universe, perhaps with slightly different fundamental properties. The universe, in this view, becomes an endless, self-renewing entity, a cosmic phoenix constantly rising from its own ashes. This idea elegantly addresses some profound questions. What happened before the Big Bang in a cyclical universe? There was no before in the linear sense, only a previous cycle. It offers a gentle reassurance of continuity, that even the ultimate end of our universe would simply be the fertile ground for a new beginning. It speaks to a deep, inherent rhythm in the cosmos, a timeless dance of creation and dissolution. However, the current observations of our universe's accelerating expansion, driven by dark energy, pose a quiet challenge to the simple bouncing model. If dark energy continues to push galaxies apart at an ever-increasing rate, it seems unlikely that gravity could ever pull everything back together for a big crunch. This doesn't entirely rule out cyclical models, but it means they would need more complex mechanisms, perhaps involving exotic forms of matter or energy that could eventually overcome dark energy's expansive pull. Or perhaps a different kind of bounce entirely. This leads us to more sophisticated, modern versions of cyclical cosmology, often found within the framework of string theory and M theory. Imagine, for a moment, that our entire three-dimensional universe, along with its time dimension, isn't all there is. What if our universe is merely a thin, shimmering rain, a membrane, floating within a higher dimensional space? This is the poetic core of ekpyrotic and cyclic universe models. In these visions, our universe as a brain might occasionally collide with another parallel brain in this higher dimensional bulk space. Imagine two vast, invisible sheets gently drifting towards each other through a cosmic void. When these two brains collide, the immense energy released from this gentle impact could manifest as the Big Bang we observe. igniting a new phase of expansion for our universe brain. After the collision, the brains might separate again, expanding away from each other for vast eons, accumulating matter and evolving, much like our universe. But eventually, they would be drawn back together, perhaps by some subtle higher dimensional force, leading to another gentle collision and another Big Bang. This creates a perpetual cycle of collisions, Big Bangs, expansions, and recollisions. A cosmic drumbeat echoing across dimensions. The beauty of this ekpyrotic model is that it offers an alternative to the traditional inflationary Big Bang, potentially explaining the smoothness and flatness of our universe without requiring a period of ultra-rapid expansion immediately after the initial singularity. It also provides a natural, if mind-bending, explanation for what happened before the Big Bang, simply the slow, quiet approach of another brain. This is a universe that is constantly renewing itself, a cosmic breath gently expanding and contracting through the vastness of higher dimensions. These brain collision models are deeply rooted in the mathematics of string theory and M theory, which suggests the universe might have more dimensions than our familiar 4-3 spatial and one-time. In these theories, particles are not point-like, but tiny vibrating strings or even multi-dimensional membranes brains. Our entire universe could be just one of these brains, existing in a larger, hidden reality. It's a truly profound thought, shifting our perspective from a self-contained universe to a single, delicate leaf on an infinite, multi-dimensional tree. Now, let us turn to a different, yet equally profound, idea about the creation of universes, the cosmic natural selection proposed by Lee Smolin, sometimes called the fecund universes hypothesis. This concept draws a gentle, intriguing parallel between the evolution of life on Earth and the evolution of universes. Imagine a universe that has the ability to reproduce itself. But how does a universe create a baby universe? Smolin's idea quietly suggests that this reproduction might happen through the formation of black holes. We know that black holes are regions of spacetime where gravity is so incredibly strong that nothing, not even light, can escape. When a massive star collapses at the end of its life, it can form a black hole. Smolin's hypothesis, however, gently posits that inside every black hole, under the extreme conditions of immense density and gravity, the very laws of physics might be retuned. Each black hole, in this speculative view, could act as a kind of cosmic seed, birthing a new baby universe on the other side of its singularity. This baby universe would then begin its own existence, expanding from a Big Bang and evolving its own set of fundamental constants. Here's the crucial, evolutionary twist: the properties of the new universe would be slightly altered. A subtle mutation from the parent universe. Now, imagine a process of natural selection unfolding not for species, but for universes. Universes that produce many black holes would be fitter in an evolutionary sense, because they would give birth to more baby universes. And what kind of universe produces many black holes? One that is very good at forming stars, which eventually collapse into black holes. This hypothesis then suggests that the laws of physics in our universe, which are so incredibly well suited for the formation of stars, are not accidental. Instead, they are the result of a long cosmic evolutionary process. Our universe is fine-tuned for star formation, and thus for black hole production. Because universes that are not good at producing black holes simply don't have many offspring over countless generations of universes. Those that were most fecund in black hole production passed on their slightly mutated, star-friendly laws of physics, leading to a cosmic environment like ours, bursting with stars and galaxies. This is a profound thought, a gentle merging of biology and cosmology, suggesting that the universe itself might be undergoing a slow, quiet process of evolution, constantly refining its own properties over unimaginable spans of time. It takes the idea of fine-tuning and gives it a dynamic, rather than static. Explanation. Our existence is not a fortunate accident, but the result of a cosmic lineage, a long, quiet process of self-improvement for the universe itself. However, this idea, while elegant and compelling, remains highly speculative. We have no direct observational evidence that new universes are born inside black holes, nor any way to test whether physical constants truly mutate across these cosmic births. It's a beautiful thought, a gentle possibility that invites deeper reflection on the universe's capacity for self-organization and evolution. Finally, let us consider an even more abstract, almost mystical, concept about the beginning of our universe, one that attempts to address the question of what was before the Big Bang by dissolving the very concept of a beginning. This is Stephen Hawking's and James Hartle's no-boundary proposal. Imagine a balloon. If you ask what is north of the North Pole, the question doesn't make sense, because the North Pole is the very top of the sphere, where north ceases to have meaning in the usual sense. The surface of the Earth has no boundary at the North Pole. Hawking and Hartley gently suggest that the universe, in the very earliest moments of the Big Bang, might be analogous to the North Pole of a space-time sphere. As you go backward in time towards the Big Bang singularity, time itself, they propose, doesn't simply stop or reach a hard edge. Instead, it behaves more like space, becoming an imaginary time dimension that curves back on itself, smoothly closing off. Much like the surface of a sphere has no edge or boundary, in this beautiful, abstract picture, there is no initial singularity, no abrupt beginning point of infinite density. Instead, the universe simply began in a perfectly smooth, well-defined quantum state, without a boundary in either space or time. The question, what happened before the Big Bang, becomes meaningless. Not because we don't know the answer, but because before simply doesn't exist in the same way. It's like asking what's south of the South Pole. There is no south, only the pole itself. This no-boundary proposal, though it attempts to describe the origin of the universe using the laws of quantum mechanics, unifying time with space in a profound way at the very beginning, it suggests a universe that simply is, without needing an external cause or a hard boundary in its initial conditions. It offers a gentle, almost meditative, resolution to the problem of creation, suggesting that the universe simply popped into existence from a state of pure quantum potential. Without any preceding time in the conventional sense, this idea, deeply rooted in quantum gravity, is immensely challenging to visualize. But it offers a profound sense of completeness to the universe's story. It suggests a cosmos that is self-contained, elegantly arising from its own internal quantum logic. Without requiring any external push or prior state, it is a universe that simply is, in a timeless, boundaryless way. As we gently conclude this chapter, allow these grand, speculative ideas to drift through your mind, whether it's a universe that bounces eternally, or one born from colliding membranes, or one that evolves through cosmic natural selection, or one that simply has no boundary at all. Each vision offers a profound sense of wonder and possibility. There is a deep peace in letting go of the need for a single, simple answer to the universe's origins, and instead, embracing the richness, the creativity, and the boundless mystery of its many possible beginnings. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet exploration of the universe's most profound mysteries. Take a soft, peaceful breath now, allowing the grand visions of cyclical universes and cosmic evolution to gently settle within your mind. We've journeyed through multiverses that are either infinitely large, or teeming with bubbles born from eternal inflation, or even those that bounce into existence from cosmic collisions. Today, we will softly enter a realm where the very building blocks of reality are not what they seem. and where the universe we perceive might be just a tiny, gentle echo of something far more complex and hidden. We will drift into the subtle world of string theory and M theory and discover how they, too, whisper of a grander multiverse, a vast landscape of possibilities. Imagine, for a moment, the smallest things you can conceive. You might think of atoms, those tiny fundamental units of matter, but quantum mechanics has already shown us that atoms are made of even smaller particles, electrons, orbiting a nucleus of protons and neutrons. And protons and neutrons, in turn, are made of even tinier particles called quarks. For a long time, physicists considered these quarks and electrons to be fundamental, indivisible points, the ultimate building blocks of everything. But what if these point particles aren't points at all? What if, at an unimaginably tiny scale, far smaller than even a quark, every particle in the universe, every electron, every photon, every quark is actually a tiny, vibrating string? This is the core, poetic idea of string theory. Imagine a single string on a musical instrument. It can vibrate in many different ways, creating different notes. In string theory, the universe is like a cosmic symphony, and the fundamental strings are the tiny performers. Each different way a string can vibrate corresponds to a different fundamental particle. One type of vibration might be an electron, another a photon, another a quark. The mass, charge, and spin of a particle, all its unique properties are determined by how its underlying string vibrates. This is a beautiful, elegant idea because it suggests a profound unity at the deepest level of reality. Instead of a zoo of many different fundamental particles, there is only one fundamental entity, the string. Everything in the universe, from the gentle glow of a distant star to the complex thoughts within your mind, is ultimately made of these tiny, vibrating strands of energy. String theory also brings a quiet, compelling answer to one of the biggest challenges in modern physics: how to unify general relativity, which describes gravity and the large-scale structure of the universe, with quantum mechanics, which describes the behavior of matter and energy at the smallest scales. These two great pillars of 20th century physics are incredibly successful in their respective domains, but they famously do not play well together. When you try to combine them, the mathematics often breaks down, yielding infinite, meaningless results. String theory offers a potential way to gently reconcile them. It naturally incorporates gravity, describing it as just another vibration of a string, the graviton. Because strings are not point-like but extended objects, their interactions are smeared out over a tiny region of space, which helps to avoid the mathematical infinities that plague other attempts at quantum gravity. It's a subtle dance, where the universe's two most fundamental descriptions find harmony. However, string theory comes with a profound, almost mystical, consequence for its equations to work out consistently. The universe must have more than our familiar 3 spatial dimensions and 1 time dimension. It requires extra dimensions, often 9 or 10 spatial dimensions in total, plus time. That's a lot more than the 4 dimensions we perceive in our everyday lives. So, where are these extra dimensions? Why don't we see them? String theory gently suggests that these extra dimensions are curled up or compactified into incredibly tiny, hidden shapes at every point in space. Imagine a garden hose from far away. It looks like a one-dimensional line. But as you get closer, you see that it also has a tiny, curled-up second dimension around its circumference. In a similar way, string theory proposes that at every point in our familiar 3-dimensional space, there are tiny, imperceptible curled-up dimensions, forming incredibly complex geometric shapes. These are often called Calabi-Yau manifolds, intricate, multi-dimensional structures that are far too small for us to ever directly observe. The shape of these curled-up extra dimensions is profoundly important. It's like the shape of a musical instrument, a violin and a guitar, though both have strings. produce different sounds because of their different shapes. In string theory, the way these extra dimensions are curled up determines the very laws of physics that we experience in our larger, observable dimensions, the type of particles that exist, their masses, the strength of the fundamental forces. All of these properties are believed to be determined by the specific geometry of these hidden, extra dimensions. Now, here's where the multiverse comes back into our quiet contemplation. The mathematical equations of string theory allow for an astronomically vast number of ways for these extra dimensions to be curled up. It's not just a few possibilities, but an almost unimaginable number of different Calabi-Yau shapes. Each different shape corresponds to a different set of physical laws in the larger, uncurled dimensions. This leads to the concept of the string theory landscape, sometimes called the landscape of vacua. Imagine a vast, undulating landscape with countless valleys and peaks. Each valley represents a different possible configuration of the extra dimensions, and thus, a different set of physical laws for a universe. Our own universe, with its specific laws of physics, occupies one tiny, specific valley in this immense landscape. The number of possible ways these dimensions can be curled up. The number of vacua or stable configurations in this landscape is often estimated to be around 10,500. This number is so astronomically vast that it defies our ordinary human comprehension. To put it into a gentle perspective, imagine the number of atoms in the entire observable universe. That's roughly 1080. The number of possible universes in this string theory landscape is not just larger, it's a number that utterly dwarfs the number of atoms in our known reality. Each of these 10,500 possibilities represents a distinct set of physical laws, a unique configuration of fundamental forces, particle masses, and even the dimensions that unfurl into existence. This staggering number, this immense landscape of possibilities, offers a gentle yet profound resolution to the fine-tuning problem we discussed earlier. If string theory is indeed a step towards the ultimate theory of everything, and if its predictions about this vast landscape are correct, then the question of why our universe has its particular laws of physics takes on a new, quiet answer. It's not necessarily that our laws are uniquely chosen by some grand cosmic principle. Instead, our universe simply occupies one incredibly tiny, specific point in this unimaginably vast landscape. We exist in one of the valleys where the conditions were just right for stars, galaxies, and life to emerge. A lucky draw in a cosmic lottery of almost infinite tickets. This landscape also provides a natural framework for the Level 2 multiverse we explored. The concept of other bubble universes with different physical laws in the context of eternal inflation. Each new bubble universe that spontaneously nucleates could correspond to a different valley or minimum energy state within this string theory landscape. As new bubbles form, they might fall into different valleys, thereby inheriting a different set of physical laws. So, the string theory landscape is like the ultimate blueprint for the multiverse, an almost infinite catalog of all possible universes. This can feel a bit overwhelming. To imagine such an unfathomable number of possible realities, each distinct and unique. But perhaps there is a quiet peace in this too. It suggests a boundless creativity at the heart of the cosmos, an almost infinite capacity for self-realization. Every possible set of consistent physical laws exists somewhere, in some form. Within this grand landscape, our universe is simply one beautiful, complex manifestation of this boundless potential. The journey to uncover these subtle truths is far from over. String theory is still a work in progress, a complex and elegant mathematical framework that is challenging to test directly. The extra dimensions are too small to detect with current technology, and the energies required to probe these tiny strings are far beyond anything our particle accelerators can achieve. Yet, the quiet whisper of its implications continues to resonate. offering a glimpse into a reality far richer and more interconnected than we might have ever dreamed. As we gently conclude this chapter, allow your mind to float with these profound concepts. Imagine the universe not as fixed and singular, but as a vast, vibrating symphony of possibilities, each note a different reality. Ponder the hidden dimensions, curled up in intricate beauty at every point in space, silently dictating the very laws that govern your existence. There is a deep peace in this boundless possibility, in letting go of the need for a single, simple answer, and instead, embracing the quiet, endless wonder of it all. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet exploration of the universe's most subtle and profound dimensions. Take another soft breath now, allowing the vast, unimaginable landscape of string theory and its myriad possible universes to settle peacefully within your mind. We've journeyed through ideas of cosmic repetition, eternally inflating bubbles, and the very fabric of reality woven from vibrating strings. Today, we will gently turn our attention to an even more abstract and beautiful concept, one that suggests the universe isn't just described by mathematics, but that it is mathematics in its purest, most elegant form. We will drift into the most encompassing vision of the multiverse level 4, the mathematical universe hypothesis. Imagine, for a moment, that everything you experience, the soft warmth of sunlight, the subtle hum of a distant sound, the complex thoughts swirling in your mind, are all just manifestations of incredibly intricate mathematical structures, not just described by equations, but inherently existing as mathematical patterns. This is the profound, almost mystical core of level 4. It suggests that our physical reality is not merely governed by mathematical laws, but that it is a mathematical structure, a self-consistent, abstract entity that exists independently of any physical substrate. To truly grasp this, let's gently revisit our earlier levels of the multiverse. Level I suggested infinite copies of our universe within an infinite space, simply because everything eventually repeats. Level 2 spoke of bubble universes, born from eternal inflation, each with different physical laws, arising from slightly different quantum conditions. Level 3, which we will touch upon more deeply in a moment, arises from quantum mechanics and suggests branching realities based on every possible outcome. Level 4, however, takes a profound leap beyond these. Encompassing them all, it posits that every conceivable mathematical structure that is internally consistent also corresponds to a real, existing physical universe. Think of it like this. Mathematics is not just a tool we use to describe the universe, it is the intrinsic language of the universe itself. And if mathematics is the fundamental language, then any story or structure that can be written perfectly within that language, without contradiction, must, in some profound sense, exist. Consider the concept of abstract mathematical objects. A perfect circle, for instance, exists as a mathematical concept, even if no perfectly round object exists in the physical world. Its properties, that all points on its circumference are equidistant from its center, are universally true within the framework of Euclidean geometry. The mathematical universe hypothesis suggests that these abstract mathematical structures are not just mental constructs in our minds, but that they have a form of objective existence. And if they exist, then perhaps they are what constitutes reality. Our universe, with its specific particles, forces, and dimensions, would simply be one particular mathematical structure among an infinite array of possibilities. It's a structure characterized by certain numbers, certain symmetries, certain equations that describe its behavior. And because this structure is internally consistent, meaning its laws don't contradict each other, it therefore exists. In the same way that the abstract concept of a perfect circle exists, This idea means that if you could somehow write down the complete mathematical description of our universe, every particle, every force, every interaction, every dimension, that complete mathematical description is the universe. And if there are other, different mathematical descriptions that are also internally consistent, then those too are other universes, existing in their own right. This concept resonates deeply with the thoughts of mathematicians and physicists who often describe the universe as being unreasonably effective at being described by mathematics. From the orbits of planets to the intricate dance of subatomic particles, mathematics provides an almost magical framework for understanding reality. Level 4 takes this intuition to its ultimate conclusion. The reason mathematics is so effective at describing the universe is because the universe is mathematics. This ultimate multiverse is not just a collection of physically distinct universes, like the bubbles of level 2. It's a collection of all possible self-consistent mathematical structures. This means that within this level 4 multiverse, there are universes where the laws of physics are entirely different from ours, not just slightly varied parameters. There could be universes where space has 5 dimensions, or 12, or even an infinite number. There could be universes where time flows in multiple directions, or where particles interact in ways we cannot even conceive. There could be universes governed by entirely different mathematical frameworks. Utterly alien to our current understanding of physics, the beauty of this level is its profound simplicity and its radical completeness. It suggests that everything that can exist does exist, provided it can be described by a consistent mathematical structure. There is no external fabric or space that these universes exist within. They simply exist as abstract mathematical entities. Our physical world, our thoughts, our consciousness, are all just manifestations of these underlying mathematical patterns. One of the most mind-bending implications of Level 4 is its connection to the very nature of reality and perception. If our universe is a mathematical structure, and if our consciousness is also somehow part of that structure, then our experience of reality is like a mathematical calculation unfolding. It hints at a universe where knowledge and existence are intrinsically linked. This ultimate form of the multiverse also offers a very deep, if unsettling, answer to the fine-tuning problem. If all possible mathematical structures exist, then it is not surprising that there is at least one structure, our universe, that is capable of supporting the emergence of consciousness to observe and understand it. Our existence is not a miracle. It's a statistical inevitability in a landscape where all consistent possibilities are actualized. However, the mathematical universe hypothesis is perhaps the most difficult level of the multiverse to test empirically. As it exists at a level of abstraction that transcends direct physical observation, it's more of a philosophical framework, a grand statement about the nature of reality, than a testable scientific theory in the conventional sense. Yet, its elegance and completeness continue to inspire deep thought and wonder among those who dare to contemplate the universe's ultimate nature. As you gently allow these concepts to drift through your mind, consider the profound implications. If reality is fundamentally mathematical, then the search for the theory of everything in physics is essentially a search for the most fundamental and elegant mathematical structure that describes our specific universe. And beyond that, there is an infinite library of other mathematical structures, other realities, waiting to be conceived. This brings a quiet, almost meditative, sense of unity to all knowledge. The physicist, the mathematician, the philosopher, and even the poet are all, in their own ways, exploring the subtle patterns and structures of existence, whether through equations, observations, logical arguments, or metaphors. We are all attempting to understand the underlying music of the universe, the subtle vibrations of its mathematical song. As we gently conclude this chapter on the boundless possibilities of the multiverse, allow your mind to simply embrace the infinite, release any need for definitive answers, any urge to grasp every detail. Just feel the profound quietness of a universe that might be infinitely larger, infinitely more diverse, and infinitely more profound than anything we can fully comprehend. There is a deep peace in this surrender, in letting go of the need to contain reality within our limited perceptions, and simply allowing ourselves to drift with the endless, gentle flow of cosmic wonder. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the boundless tapestry of existence. Take another soft, peaceful breath now, allowing the profound concept of a mathematical universe, where every consistent structure quietly exists. To settle gently within your mind, we've explored the grand, sweeping ideas of multiple universes, each a variation on the theme of reality. Today, we will softly shift our gaze from the vast, abstract realms of the multiverse to something much more immediate, something that defines our very perception of the world around us: light. Imagine for a moment the world without light. It would be an endless, silent darkness, a void where nothing is seen, nothing truly known. Light is the gentle messenger that paints our reality, allowing us to see the vibrant colors of a sunrise, the delicate patterns on a leaf, the warm glow of a distant fire. It is so fundamental to our experience. Yet its true nature is far more mysterious and wondrous than our everyday senses might suggest. For centuries, the nature of light was a profound puzzle. Was it a stream of tiny particles, like miniature bullets traveling through space, or was it a wave, rippling through an invisible medium? Much like waves on water, Isaac Newton, the great mind who mapped the laws of motion and gravity, favored the particle theory, envisioning light as corpuscles, tiny, discrete packets. Later, brilliant experiments by scientists like Thomas Young showed light behaving clearly as a wave, creating interference patterns much like ripples from two stones dropped in a pond. It seemed like an either-or question, a scientific debate that raged for generations, but the universe, in its gentle wisdom, often reveals that reality is far more nuanced than our simple categories. The true nature of light, we now understand, is a beautiful and perplexing duality. Light is both a wave and a particle at the same time. Imagine a single ray of light, a gentle beam filtering through a window. When it travels through space, it behaves like a wave, spreading out, bending around obstacles, and creating patterns of interference. But when it interacts with matter, when it hits a screen, or is absorbed by a sensor, or strikes your eye, it behaves like a discrete packet of energy, a tiny bundle called a photon. It's as if light chooses its costume depending on the scene it's playing in. This wave-particle duality is not just a strange quirk of light, it's a fundamental principle of quantum mechanics, which governs the behavior of matter and energy at the smallest scales. Photons are the universe's most tireless travelers. They are born in the hearts of stars, in the fiery explosions of supernovae, and in the quiet dance of electrons shifting energy levels within atoms. Once born, they embark on journeys that can span unimaginable distances and eons of time. And they are the universe's fastest messengers. Nothing in our universe can travel faster than light in a vacuum. This is a fundamental speed limit, a cosmic constant. Approximately 299,792,458 meters per second. It's a number so vast it almost loses meaning, but it underpins everything we observe about the cosmos. Consider the gentle light reaching your eyes from the sun. That light, those tiny photons, were born about 8 minutes ago in the sun's fiery core. They traveled 150 million kilometers to reach you. A cosmic journey of just a few minutes. The sunlight warming your skin is literally light from the past, a gentle touch from a moment that has already passed. But now, let your mind drift to something far more distant. Something truly ancient. Look up at the night sky, if you can, and find a tiny, twinkling star. That star might be Proxima Centauri. the nearest star to our Sun. The light from Proxima Centauri took over 4 years to reach Earth. So, when you look at Proxima Centauri, you are not seeing it as it is now, but as it was 4 years ago. You are literally looking into the past. The light carries with it a quiet record of a moment that occurred long before your current breath. Now, extend this idea to the immense distances of galaxies. When we gaze at the Andromeda Galaxy, the nearest large spiral galaxy to our own, we are seeing light that has traveled for approximately 2.5 million years. This means the Andromeda Galaxy we observe is how it appeared 2.5 million years ago, a time when early human ancestors were just beginning to walk the Earth. The light from Andromeda is a silent time capsule, carrying the image of a distant past directly to our eyes. And then, there are the truly ancient lights, the most distant whispers from the universe's infancy. The powerful telescopes we discussed earlier, like the Hubble Space Telescope and the new James Webb Space Telescope, are cosmic time machines. They collect light from galaxies that are billions of light years away. When we observe these distant galaxies, we are seeing them not just as they are now, but as they were billions of years ago, when the universe was much younger. When these galaxies were just forming, we are witnessing the universe's quiet evolution, playing out in slow motion before our very eyes. Painted by the ancient light reaching us now, this is why looking at the night sky is like looking into a vast, layered history book. Each point of light, whether a nearby star or a distant galaxy, is a gentle echo from a different moment in time. The deeper we look into space, the further back in time we see. The universe is not just vast in its expanse, but also in its temporal depth, a living archive of its own past, recorded and delivered by photons. This concept of light from the past also subtly shapes our understanding of the universe's edge. When we speak of the observable universe, we are not talking about the physical edge of space itself, but rather the limit of how far light has been able to travel to us since the Big Bang. The universe may stretch infinitely beyond that, but light from those regions simply hasn't had enough time to reach us yet. So, our observable universe is a sphere of light, defined by the journey of photons since the dawn of time. Consider, too, how light connects us not just to the distant past, but to the very origins of the universe. We briefly touched upon the cosmic microwave background radiation, the faint afterglow of the Big Bang. This ancient light, redshifted and cooled over billions of years of expansion, is the oldest light we can detect. It's a gentle, uniform hum of microwaves coming from every direction, a relic from a time when the universe was only about 380,000 years old. A hot, dense plasma too opaque for light to travel freely. As the universe expanded and cooled, it became transparent, and this light was finally able to stream across the cosmos. When we detect the CMB, we are literally seeing the universe at its infancy, a profound connection to the moment of creation itself. This light, these photons, are not just passive observers, they carry immense amounts of information. By analyzing the different wavelengths of light, its spectrum, we can deduce the chemical composition of distant stars and galaxies, their temperature, their velocity, and even the strength of magnetic fields in distant nebulae. It's like listening to the unique melody of each cosmic object, each note revealing a hidden truth about its nature. The universe communicates with us through light, a silent, eloquent conversation spanning billions of years. And what about light's gentle touch on our own existence without light? There would be no photosynthesis, the fundamental process that powers almost all life on Earth, converting sunlight into the energy that fuels plants. And ultimately, us. Our very perception of reality is built upon light. Our eyes are exquisitely designed to capture photons, transforming their energy into the intricate images we perceive. We are beings bathed in light, shaped by its presence, utterly reliant on its ceaseless journey, As our gentle exploration of light concludes, allow yourself to feel this profound connection. You are receiving messages from the distant past, from the fiery hearts of stars, from the very edge of the observable universe, all delivered by these tireless, silent photons. There is a deep peace in this interconnectedness, in knowing that the light warming your skin, illuminating your path, is the very same light that has journeyed across cosmic eons, binding you to the vast, ancient, and ever unfolding story of the universe. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet exploration of the cosmos. Take another soft, peaceful breath now, allowing the profound duality of light, its nature as both wave and particle, and its role as a messenger from the distant past, to gently settle within your mind. We've seen how light connects us to ancient stars in the very beginning of the universe. Today, we will softly shift our focus from light itself to the stage upon which its grand journey unfolds time. Imagine time, not as a rigid, unyielding river always flowing in one direction, but as something more fluid, more dynamic, almost alive. In our everyday experience, time feels absolute. A second is a second, a minute, everywhere, for everyone. We mark its passage with clocks and calendars, and it seems to relentlessly push us from the past, through the present, and into the future. This intuitive understanding, often attributed to Isaac Newton, saw time as a universal, unchangeable backdrop against which all events played out. It was a cosmic ticking clock, always keeping the same rhythm, everywhere. But the universe, in its gentle complexity, often defies our simplest intuitions, just as light revealed its dual nature. Time, too, holds secrets far stranger than our everyday perception. The revolutionary insights of Albert Einstein, particularly his theories of relativity, profoundly reshaped our understanding of time, transforming it from a mere backdrop into an active participant in the cosmic dance. Einstein's first great revelation came with his special theory of relativity in 1905. It introduced the astonishing concept that time is not absolute, it is relative. It can stretch and contract, depending on an observer's motion. This phenomenon is known as time dilation. Imagine you are watching a friend fly past you in a spaceship, traveling at an incredibly high speed, a significant fraction of the speed of light. From your perspective, watching from a stationary point, time on your friend's spaceship would appear to slow down. Their clock would tick more slowly. Their movements would appear more sluggish, and they would age more slowly than you. And here's the quiet, mind-bending part from your friend's perspective inside the spaceship. Everything on Earth would appear to be moving in slow motion. Their time feels normal to them, but your time appears dilated. This isn't just a trick of perception or an optical illusion. It's a real physical effect, a fundamental property of space-time. Time literally passes differently for observers in relative motion. The faster you move through space, the slower you move through time. And this effect has been rigorously proven by countless experiments. Atomic clocks flown on high-speed jets, or even those on GPS satellites orbiting Earth, tick slightly slower than identical clocks on the ground. Though the difference is tiny at everyday speeds, it accumulates, and engineers must account for it to ensure our navigation systems work accurately. This idea might feel strange, almost like a dream, but allow yourself to simply float with the concept. Imagine the universe allowing different rhythms of time. Depending on how fast you're dancing through it, it suggests that your personal journey through time is unique, subtly shaped by your own motion. Then came Einstein's general theory of relativity in 1915, which unveiled an even more profound secret of time gravity. Also bends time, not just space, but time itself can be warped by the presence of mass and energy. This phenomenon is known as gravitational time dilation. Imagine a massive object, like a star or a planet. Its immense mass creates a dent or a curve in the fabric of space-time. Much like a heavy bowling ball placed on a stretched rubber sheet, the deeper the gravitational well, the more profoundly time is affected. Near a massive object, time passes more slowly than it does further away. For example, time on Earth, even for you right now, passes ever so slightly slower than it would in deep space, far away from any strong gravitational pull. This difference is incredibly tiny, imperceptible in our daily lives, but consider a place with truly extreme gravity, like the event horizon of a black hole. A black hole is a region where gravity is so intense that nothing, not even light, can escape. If you were to observe someone falling into a black hole from a safe distance, you would see their clock ticking slower and slower as they approach the event horizon. From your perspective, time for them would appear to slow down almost to a standstill, becoming infinitely dilated as they cross the point of no return. You would never actually see them cross the event horizon. Their image would simply fade. Frozen in time, eternally suspended just outside. But from the perspective of the person falling into the black hole, their own time would feel perfectly normal. They would cross the event horizon in a finite amount of their own time, unaware of the profound time dilation observed by someone far away. This is one of the most mind-bending implications of general relativity, a quiet testament to the universe's ability to create entirely different temporal experiences. These revelations about time, its relativity to motion, and its warping by gravity, tell us that time is not a separate entity, but is intrinsically woven together with space, forming a unified four-dimensional fabric called space-time. Imagine reality as a vast, flexible sheet, and every event, every moment, is a point on this sheet. The presence of mass and energy creates curves in this sheet, and these curves dictate not only how objects move through space, but also how they move through time. This means that our journey through time is not a simple linear progression from past to future. It is a path influenced by the gravitational landscape around us and by our own speed through space. It's like walking on a vast, undulating terrain, where some paths are steeper, some are flatter, and your pace is subtly altered by the landscape itself. The question then arises if time can slow down or speed up. Does it have a true beginning? And could it have an end? Our current understanding, based on the Big Bang Theory, suggests that time itself began at the moment of the Big Bang, approximately 13.8 billion years ago. Before the Big Bang, the concept of time as we understand it may not have existed. It's not that there was a before the Big Bang in a temporal sense, but rather that time itself emerged with the universe. This is a profound, almost mystical thought, suggesting that time is not an eternal given, but a property of our universe, born with it. And what about the end of time? If our universe continues to expand, driven by dark energy, it might eventually stretch to a state of extreme cold and emptiness, where stars burn out, black holes evaporate, and all matter becomes infinitely dispersed. In this far, far future, often called the Big Freeze or heat death, the universe would become a vast, cold, dark, and increasingly still place. In such a scenario, where all activity ceases and no processes can occur, the very concept of time might gradually lose its meaning, perhaps simply fading into an eternal stillness. However, other cosmological models, as we gently touched upon in our discussions of cyclical universes, suggest that time might be part of an endless cycle, endlessly beginning and ending, or perhaps simply having no true beginning or end in a deeper, more abstract sense. These are the profound questions that continue to invite quiet contemplation, reminding us that our understanding of time is still evolving, still gently pushing against the edges of the known. Consider, too, the philosophical implications of time. If time is relative, then the present moment is not a universal constant. Your now is different from a now on a distant galaxy, or even on a high-speed spacecraft. This suggests a universe where reality isn't unfolding simultaneously for everyone, but rather as a mosaic of individualized temporal experiences. It's a gentle reminder of the subjective nature of our own reality. As our gentle exploration of time concludes, allow your mind to simply float with these profound ideas. Imagine time not as a rigid tick-tock, but as a flexible ribbon, bending and stretching with the universe's grand dance. Feel the subtle currents of gravitational time dilation. Even in the quiet space around you, there is a deep peace in realizing that your personal journey through time is unique, intricately woven into the very fabric of space-time. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the profound mysteries of the cosmos. Take another soft, peaceful breath now, allowing the flexible nature of time, its subtle stretching and bending under the influence of speed and gravity, to settle gently within your mind. We've seen how time is not merely a backdrop, but an active participant in the universe's grand dance, intricately woven into the fabric of space-time itself. Today, we will softly turn our attention to the very stage of this cosmic drama space. Imagine, for a moment, that space is not just an empty, passive void where things happen. For centuries, this was the prevailing view. Space was like a vast, invisible container, a three-dimensional grid, perfectly still and unchanging, within which stars, planets, and galaxies moved. This intuitive understanding of space, again, deeply influenced by Isaac Newton, pictured it as an absolute, rigid expanse, extending infinitely in all directions. It was the silent, unchanging arena for all of existence. But once more, the universe, in its gentle complexity, defies our simplest intuitions. Just as Einstein revolutionized our understanding of time, he also profoundly reshaped our view of space. With his general theory of relativity, he revealed that space is not a mere backdrop. It is a dynamic, active participant, deeply intertwined with matter and energy. Imagine space as a vast, flexible fabric, like a colossal, stretched rubber sheet. Now, place a heavy object, like a bowling ball, onto this sheet. What happens? The sheet doesn't remain flat. It creates a dent or a curve around the bowling ball, according to Einstein. This is precisely what massive objects do to space and time. They warp and curve the fabric of space-time around them. This warping of space-time is what we experience as gravity. We often think of gravity as a force, a mysterious pull that objects exert on each other. But in Einstein's elegant description, gravity isn't a force in the traditional sense. Instead, objects move along the shortest possible paths within this curved space-time. Think of a marble rolling across that stretched rubber sheet. If the sheet is flat, the marble rolls in a straight line, but if there's a bowling ball creating a dent, the marble's path will curve as it approaches the bowling ball, not because the bowling ball is pulling it, but because the sheet itself is curved. The marble is still trying to go straight, but it's going straight through curved space. This is how the Earth orbits the Sun. The Sun's enormous mass creates a significant curve in the space-time around it. Earth isn't being pulled by an invisible tether. It's simply following the curves and dents in the space-time fabric that the Sun has created. Our planet is constantly falling through curved space around the Sun. This profound idea transformed gravity from a mysterious force into a geometrical property of space itself. It's a gentle, elegant dance between matter and the very fabric of reality. This concept means that space is not empty. Even what appears to be the most profound vacuum is subtly shaped by the presence of all the mass and energy within it. Every star, every planet, every galaxy indeed. Every particle contributes to the gentle warping and stretching of the cosmic fabric. And in turn, this warped fabric dictates how everything moves. It's a silent, continuous conversation between content and container, But space is even more dynamic than just being warped by massive objects. It is also expanding. We briefly touched upon this when discussing the Big Bang. The idea that the universe is expanding means that the very fabric of space itself is stretching, carrying galaxies further apart from each other. Like dots drawn on the surface of an inflating balloon, it's not that galaxies are moving through space, it's that space between the galaxies is growing. This expansion is not uniform, it's accelerating. Driven by the mysterious dark energy we contemplated earlier, imagine that cosmic rubber sheet not only being dented by bowling balls, but also being gently, universally stretched from within, accelerating its expansion over vast distances. This stretching means that the universe is not a static painting. It's a living, breathing canvas, constantly growing, constantly unfolding. Now, let us turn our attention to an even more subtle and profound aspect of space, its nature, at the smallest possible scales. When we speak of empty space, we often imagine nothingness, but according to quantum mechanics, nothingness is rarely truly empty, at unimaginably tiny scales, below the reach of our most powerful microscopes. Empty space is a seething, bubbling cauldron of activity. This is the realm of the quantum foam or vacuum fluctuations. Imagine a seemingly still pond from a distance. It looks perfectly calm, but if you zoom in very, very closely, you might see tiny, ephemeral bubbles constantly forming and popping on the surface. In a similar way, quantum theory suggests that empty space is not truly empty. Instead, it is filled with virtual particles constantly popping into and out of existence in fleeting moments. Pairs of particles and antiparticles spontaneously appear, exist for an unimaginably brief instant, and then annihilate each other. Returning their energy to the vacuum, this happens all the time, everywhere, even in the darkest, coldest voids of space. This constant bubbling of virtual particles is driven by the Heisenberg uncertainty principle, a fundamental tenet of quantum mechanics that tells us we cannot perfectly know certain pairs of properties at the same time, like a particle's position and momentum, or its energy and lifetime. This means that for a tiny, fleeting moment, the vacuum can borrow energy to create these virtual particles. As long as they disappear quickly enough to satisfy the uncertainty principle, it's as if the universe is constantly experimenting with creation, testing the boundaries of existence at the very edges of reality. This quantum foam is not just a theoretical curiosity. Its effects are subtly detectable. For instance, the Casimir effect demonstrates that two uncharged, parallel metal plates placed very close together in a vacuum will experience a small attractive force. This force arises because the plates restrict the types of virtual particles that can pop into existence between them, creating a slight imbalance in the quantum vacuum pressure. Pushing the plates together, it's a quiet whisper from the void, confirming its bustling, unseen activity. This means that space, at its most fundamental level, is not smooth and continuous. It might be incredibly bumpy and foamy, a chaotic tapestry of fleeting quantum events. It's like looking at a seemingly smooth fabric, but under a powerful microscope. You see it's actually made of countless intertwining threads and tiny gaps. Furthermore, some theories, particularly those attempting to unify gravity with quantum mechanics, like loop quantum gravity, suggest that space itself might not be continuous at all, but instead be made of discrete, tiny, indivisible units, like pixels on a screen. This is a profound idea if space is truly quantized. Then there's a smallest possible unit of length, a cosmic pixel, below which space simply doesn't exist. This would mean that the smooth fabric we perceive is merely an emergent property of countless tiny, discrete chunks of space. Much like a smooth image on a screen is made of individual pixels. This leads to fascinating questions. If space is fundamentally discrete, what does that mean for how the universe works at its absolute smallest scales? And if space itself is quantized, what does that imply for the nature of time, which is so deeply intertwined with it? These are questions that scientists continue to gently ponder, pushing the boundaries of our understanding into realms where our everyday intuition no longer applies. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes counterintuitive ideas about space. Imagine the invisible curves in spacetime, subtly guiding the dance of planets and stars. Feel the quiet, ceaseless bubbling of the quantum foam, a hidden ocean of fleeting possibilities even in the deepest void, and consider the possibility that space itself, the very canvas of our reality, might be woven from discrete, tiny threads, a cosmic tapestry of unimaginable intricacy. There's a deep peace in this boundless complexity, in letting go of rigid notions and embracing the universe's gentle, dynamic nature. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound enigmas. Take another soft, peaceful breath now, allowing the dynamic nature of space, its graceful curving by gravity, its accelerating expansion, and the ceaseless bubbling of the quantum foam to settle gently within your mind. We've explored the grand stages of cosmic existence, from the infinite multiverse to the subtle fabric of space-time. Today, we will softly turn our gaze inward, to the most intimate and elusive mystery of all consciousness. Imagine, for a moment, the simple act of being aware, the gentle warmth of the air on your skin, the subtle sound of your own breath, the quiet thoughts that drift through your mind. This subjective experience, this feeling of you being present and perceiving the world, is consciousness. It is, perhaps, the ultimate frontier of human inquiry, a mystery that philosophers and scientists have quietly pondered for millennia. How does a collection of physical cells, neurons and synapses, give rise to the rich, vibrant, and utterly personal experience of being alive? For a long time, many in science approach consciousness as an emergent property of the brain, something that arises from the complex interactions of billions of neurons firing in intricate patterns. It's like a symphony emerging from the individual notes played by each instrument. The music isn't in any single note, but in their collective harmony. In this view, consciousness is a sophisticated biological function, a product of evolution, giving us the ability to navigate our environment, plan for the future, and understand our place in the world. It is, in essence, the brain doing its job at its most advanced level. However, this traditional view faces what philosophers call the hard problem of consciousness. It's not so much a problem of how the brain processes information. We have increasingly sophisticated models for that. But why it feels like anything at all. Why isn't a brain, however complex, just a sophisticated calculator, processing inputs and producing outputs without any inner subjective experience? Why does it feel like something to be you? Why the redness of red, the sweetness of sugar, the pang of longing? This qualitative, subjective aspect of experience is often called qualia, and it remains a quiet, persistent challenge to purely materialistic explanations. This hard problem has led many to gently explore more profound and often speculative ideas about consciousness. One such idea suggests that consciousness isn't merely an emergent property of complex biological systems, but a more fundamental aspect of reality, perhaps existing in a rudimentary form even at the most basic levels of the universe. This is the realm of panpsychism. Imagine, if you will, that the very building blocks of the universe, the tiny particles, the fields, the energy, possess some form of proto-consciousness, a fundamental capacity for experience, however simple. It's not that a single electron is conscious in the way a human is, but rather that it carries a tiny, infinitesimal spark of awareness, a raw ingredient from which more complex forms of consciousness can emerge. Think of it like water, A single molecule of water doesn't have wetness, but when billions of them come together in a certain way, wetness emerges. Panpsychism suggests that consciousness might be like that, an intrinsic property that scales up with complexity. In this quiet view, consciousness isn't something that mysteriously appears when brains become complex enough. It's something that is present all along, at every level, simply becoming more integrated and sophisticated as matter organizes itself into living systems, and then into complex brains. It's a universe where awareness is not an anomaly, but a fundamental texture of reality, a gentle hum resonating through all existence. This idea helps to bridge the gap between mind and matter, offering a subtle sense of unity. If consciousness is fundamental, then the physical world and our subjective experience are not two separate realms, but different aspects of the same underlying reality. It suggests that perhaps the very quantum foam we discussed, those fleeting virtual particles popping into and out of existence, hold within them a whisper of proto-experience, a primordial form of feeling or being. However, panpsychism also raises its own gentle questions. How do these tiny sparks of awareness combine to form the rich, integrated consciousness of a human being? This is known as the combination problem. And how can we possibly test such an idea? It remains a deep philosophical exploration, a quiet invitation to consider consciousness not just as a product, but as an intrinsic feature of the cosmos, another fascinating and deeply profound. Perspective comes from the world of quantum mechanics itself, the very theory that describes the universe at its smallest scales. We've seen how quantum particles exist in a state of superposition, meaning they can be in multiple states at once until they are observed, and how measurement seems to collapse this superposition into a single, definite outcome. This peculiar behavior has led some, including brilliant minds like Eugene Wigner, to suggest that consciousness itself plays a role in this collapse. Imagine a quantum particle existing in a blurred state of possibility. According to this interpretation, it's not simply a detector or an instrument that performs the measurement and causes the collapse, but the act of a conscious observer becoming aware of the outcome. It's as if the universe's reality only fully crystallizes when consciousness looks at it. This is sometimes called the consciousness causes collapse interpretation. Or more broadly, the idea that consciousness is somehow intertwined with the fundamental processes of the universe. This perspective implies a truly profound relationship between mind and matter, suggesting that consciousness is not just an epiphenomenon, a mere passenger in the cosmic journey, but an active participant in shaping reality at its deepest level. It suggests that the act of observation, the quiet moment of awareness, is not passive, but a powerful interaction with the quantum realm. This interpretation is deeply debated within the physics community, and many physicists prefer interpretations that do not invoke consciousness directly in the collapse process, such as the many worlds interpretation, which we will gently explore in the next chapter. But the idea that consciousness might be more than just a biological byproduct, that it might be woven into the very fabric of quantum reality, is a deeply unsettling yet alluring possibility. A quiet whisper that our inner world and the outer cosmos are intrinsically connected. This brings us to a more general, yet equally profound question: is our consciousness limited to our physical brain, or could it be connected to something larger, something more cosmic? This is where the boundaries between science, philosophy, and even spirituality begin to gently blur. Some theories, often inspired by ancient wisdom traditions, suggest that individual consciousness is merely a small wave in a vast cosmic ocean of consciousness, a universal field of awareness that permeates all of reality. Imagine that just as the electromagnetic field permeates space and carries light waves, there might be a fundamental field of consciousness that permeates the universe. Our individual brains would then act as receivers or antennae, tuning into and localizing this larger field, much like a radio tunes into specific frequencies from an ambient radio wave. In this view, Consciousness isn't produced by the brain, but rather filtered or expressed through it. This concept suggests that consciousness is not confined to individual beings, but is a fundamental property of the cosmos, from which all individual awareness emerges and to which it ultimately returns. It implies a deep interconnectedness, a profound unity among all conscious beings and indeed with the universe itself. It's a comforting thought, a gentle reassurance that our individual awareness is not isolated, but part of a grander, more encompassing whole. This idea, while beautiful and deeply resonant for many, is currently beyond the realm of scientific measurement and empirical verification. It belongs more to the realm of philosophical contemplation and personal experience. Yet, it offers a powerful framework for understanding our place in the universe, suggesting that our inner world and the outer cosmos are not separate, but two sides of the same profound reality. As we gently conclude this chapter, allow your mind to drift with these profound questions about consciousness. Ponder the miracle of your own awareness, the feeling of being you in this vast and mysterious universe. Consider the possibility that consciousness might be more than just a biological accident, that it might be a fundamental aspect of reality, a silent, pervasive hum throughout the cosmos. There is a deep peace in this boundless mystery, in letting go of the need for definitive answers and simply embracing the profound wonder of your own conscious existence. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most mind-bending ideas. Take another soft, peaceful breath now, allowing the profound whispers of consciousness, its potential as a fundamental aspect of reality, or its role in shaping the quantum realm, to gently settle within your mind. We've journeyed through the vastness of space, the elasticity of time, and the elusive nature of awareness. Today, we will softly explore an idea that suggests not just multiple universes, but multiple realities unfolding from every single moment. A concept that intertwines the very act of observation with the fabric of existence. We will drift into the subtle, branching world of the many worlds interpretation of quantum mechanics. Imagine a tiny quantum particle, perhaps an electron, before we observe it. Quantum mechanics tells us it exists in a state of superposition. This means it's not in one definite place or one definite state, but rather exists in all its possible states simultaneously. It's like a ghostly blur of possibilities. It might be spinning clockwise and counterclockwise at the same time, or be in two different locations at once. So this is the peculiar, counterintuitive nature of the quantum realm. Now, imagine we perform an observation or a measurement on this particle, according to the traditional understanding of quantum mechanics. This act of observation collapses the superposition. The ghostly blur of possibilities instantly snaps into a single, definite reality. The electron is now spinning either clockwise or counterclockwise, either here or there, no longer both. This collapse of the wave function is essential, yet deeply mysterious aspect of quantum theory. What causes it? And why does the universe suddenly choose one outcome over all others? This is where the many worlds interpretation MWI, first proposed by Hugh Everett III in 1957, offers a profoundly different, and arguably more elegant, explanation. Instead of the wave function collapsing, MWI suggests that it never collapses at all. Instead, at every moment when a quantum choice is made, or a measurement is performed, the universe splits or branches into multiple, parallel realities. Imagine that electron in superposition, existing in two possible states spinning clockwise or spinning counterclockwise. When you observe it, MWI says that the universe doesn't choose one outcome. Instead, it branches in one branch of reality. You observe the electrons spinning clockwise. In another, parallel branch of reality, you observe the electrons spinning counterclockwise. Both outcomes are equally real, simply existing in different, non-interacting universes. This branching doesn't just happen for tiny particles, it happens for every quantum event, all the time, everywhere. Consider a more macroscopic example, often used to illustrate the strangeness of quantum superposition: Schrödinger's cat. Imagine a cat placed in a sealed box with a vial of poison that will break only if a single radioactive atom decays, according to quantum mechanics. Until the box is opened and observed, the atom is in a superposition of decayed and not decayed states. This means the cat, too, is in a superposition of being both alive and dead simultaneously. In the traditional view, opening the box collapses the superposition, and the cat is definitively found to be either alive or dead. But MBWI says something far more radical. When you open the box, the universe splits in one new branch. You open the box and find the cat alive in another parallel branch. You open the box and find the cat dead, and you, the observer, also split. There's a version of you in the alive cat branch and a version of you in the dead cat branch. Both versions of you are equally real, having experienced different outcomes. This implies an unimaginably vast, constantly branching multiverse or many worlds. Every decision you make, every flicker of a quantum particle, every roll of a dice, all of these moments cause the universe to split into new, distinct branches, each representing a different possible outcome. Your life, your history, is not a single, linear path, but an infinitely branching tree, with countless versions of you living out every conceivable permutation of your existence in parallel realities. The beauty of MWI is that it resolves the collapse problem of quantum mechanics by simply removing it. The wave function never collapses. It always evolves linearly, endlessly branching into all possible outcomes. It offers a mathematically elegant way to interpret quantum reality, taking the strange implications of superposition to their ultimate logical conclusion. It suggests that all the possibilities we imagine, all the roads not taken, are in fact being lived out by other versions of ourselves in other branches of reality. However, the many worlds interpretation is also incredibly challenging to visualize and accept intuitively. It means that there is an unfathomable number of yous out there, living out countless variations of your life. These other branches are fundamentally inaccessible to us. We can never communicate with our other selves, never observe the parallel universes directly. They exist in a state of quantum decoherence, meaning their wave functions have effectively separated and can no longer interfere with each other. It's as if they drift apart, forever, out of reach. The question of whether the many worlds interpretation is true is a deep and ongoing debate in physics. There is no definitive experimental way to distinguish it from other interpretations of quantum mechanics. Yet, its elegance and its ability to resolve certain quantum paradoxes make it a compelling and widely discussed idea among cosmologists and quantum theorists. It offers a profound sense of cosmic abundance, suggesting that reality is far richer and more diverse than our single linear experience might suggest. This perspective can also be surprisingly calming. If every possibility is realized in some branch of reality, then perhaps there's no need to agonize over every decision. Every choice, every path, is explored somewhere. It offers a gentle reassurance that the universe is constantly playing out all its possibilities, a boundless cosmic drama unfolding in countless parallel acts as you gently allow these concepts to drift through your mind. Consider the profound implications of a constantly branching reality. Imagine the subtle echoes of choices not made, playing out in universes forever beyond your direct reach. Feel the quiet awe of a universe that never truly collapses its possibilities, but instead manifests them all in an endless, intricate tapestry of parallel worlds. There is a deep peace in this boundless potential, in letting go of the need for a single, fixed reality. and simply embracing the infinite possibilities of existence. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most enigmatic concepts. Take another soft, peaceful breath now, allowing the profound notion of parallel realities, constantly branching from every quantum choice, to settle gently within your mind. We've explored the many worlds interpretation, where every possibility unfolds in its own distinct universe. Today, we will softly delve into a related yet subtly different idea, one that asks whether our reality might be something entirely unexpected, something crafted, something simulated. We will drift into the intriguing whispers of the simulation hypothesis. Imagine for a moment that everything you perceive, the gentle warmth of the sun, the intricate patterns of a leaf, the very thoughts forming in your mind, the vastness of the cosmos stretching out before you, is not fundamentally physical in the way we traditionally understand it. What if it is all, in essence, a sophisticated program, a meticulously crafted simulation running on an unimaginably powerful computer? This is the core, deeply unsettling yet equally alluring idea of the simulation hypothesis. This concept isn't entirely new. It echoes ancient philosophical questions about the nature of reality. Often posed as, are we dreaming, or is this all an illusion? But the modern simulation hypothesis gives these questions a technological, scientific twist, rooted in our own accelerating advancements in computing and virtual reality. Consider our own technological trajectory. Over just a few decades, we've moved from simple video games to incredibly complex virtual worlds that capable of simulating vast landscapes, intricate physics, and even rudimentary artificial intelligences. As our computational power continues to grow exponentially, it's not unreasonable to imagine a future where our descendants, or some advanced civilization, possess such immense computing capabilities that they could simulate entire universes, complete with conscious beings within them. This leads to a compelling argument, famously articulated by philosopher Nick Bostrom, often presented as a trilemma. It is almost certain that all civilizations at our current stage of development go extinct before becoming technologically mature enough to run vast ancestor simulations. This is a pessimistic possibility, suggesting that humanity or similar civilizations simply don't survive long enough to reach that level of computational power. Perhaps we destroy ourselves through war, ecological collapse, or some unforeseen cosmic event. Any technologically mature civilization that reaches the capacity to run ancestor simulations will almost certainly choose not to run them. This is a more optimistic, or perhaps perplexing, possibility. Why would a super-advanced civilization, capable of such a feat, choose not to explore the full extent of their capabilities? Perhaps there are ethical considerations, or perhaps they find no compelling reason to do so. We are almost certainly living in a computer simulation. If the first two possibilities are unlikely, then the third becomes statistically probable if there are countless technologically mature civilizations across the multiverse, and if at least some of them choose to run even a small number of ancestor simulations. Then the number of simulated realities would vastly outnumber the single base reality from which they originated. In this scenario, it becomes overwhelmingly more likely that we are one of the simulated minds rather than the rare, original ones. This idea challenges our most fundamental assumptions about reality. If we are in a simulation, what does that mean for our free will? For the meaning of our lives? For the very fabric of our universe? Imagine the universe's seemingly fundamental constants and laws of physics. If we are in a simulation, these laws could simply be the programmed rules of the simulation, parameters set by the programmers in the base reality. Our dark matter and dark energy could be merely glitches, computational artifacts, or placeholders within the code. The limitations of our speed of light, the Planck length, the smallest possible unit of distance, or the fundamental uncertainty of quantum mechanics could all be clever ways to optimize computational resources within the simulation, preventing it from having to render every single detail at every single moment. This isn't necessarily a cold, dispassionate thought. It could be seen as a new kind of wonder. If our reality is a simulation, then it implies the existence of a higher reality, a base universe beyond our own, where beings of unimaginable intelligence and power exist. It subtly connects us to a larger hierarchy of existence, a nested Russian doll of realities. The concept might even offer a gentle explanation for some of the universe's perplexing fine-tuning that we discussed in earlier chapters. If the universe's constants are so precisely set to allow for life, perhaps it's because these are the parameters chosen by the simulators to allow for complex, conscious entities like us to emerge and evolve within their simulated environment. We might be part of a cosmic experiment, a grand scientific inquiry, or simply a form of advanced entertainment for the beings in the base reality. But how could we possibly test such a hypothesis? How could we distinguish between a simulated reality and a base reality? This is one of the greatest challenges. Some suggest looking for subtle glitches in the fabric of reality, tiny inconsistencies in physical laws, or anomalies that hint at a finite computational power. For example, some physicists have playfully suggested looking for evidence of a pixelated universe at extremely small scales, or for numerical limits to the complexity of the cosmos that hint at computational constraints. Others look for strange patterns in cosmological data, or unexpected limits to the maximum energy of cosmic rays that might be due to the grid size of the simulation. However, the programmers could be infinitely clever, constantly patching any detectable glitches, or designing the simulation so perfectly that its underlying code is utterly indistinguishable from a real physical universe. And in that case, the question might remain an eternal mystery, a profound philosophical puzzle that can never be definitively solved. The simulation hypothesis also gently nudges us to consider the nature of our own consciousness within this framework. If our brains are simulated, are our experiences any less real? If the qualia of red or the feeling of joy are simply lines of code or emergent properties of a vast algorithm, does that diminish their profound personal impact? Most proponents of the hypothesis would argue no. Our subjective experience, our suffering, our joy, our love, these would be utterly real within the simulation, just as real as the experiences of characters within a highly immersive virtual reality game are real to them. This perspective can be deeply liberating if we are in a simulation. Perhaps the rules are not as fixed as we imagine. Perhaps there are ways to understand the code of our reality, to transcend its perceived limitations, or even to communicate with the programmers. It's a whimsical thought, a quiet invitation to see our universe not just as a given, but as a potential creation, a masterpiece of cosmic engineering. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes unsettling ideas about the simulation hypothesis. Ponder the possibility that your reality, your very existence, is part of a grand cosmic program. Consider the subtle implications for consciousness, for the laws of physics, and for our place in a potentially nested hierarchy of realities. There is a deep peace in this boundless mystery, in letting go of rigid definitions of what is real and embracing the universe's gentle capacity for infinite possibilities. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound and subtle concepts. Take another soft, peaceful breath now, allowing the intriguing idea of a simulated reality, with its layers of existence and hidden programmers, to gently settle within your mind. We've traversed the vastness of space, the fluidity of time, the elusive nature of consciousness, and the branching possibilities of multiple worlds. Today, we will softly explore an idea that brings us full circle, connecting the grand scale of the cosmos with the intimate scale of our own perceptions. The concept of holographic reality. Imagine, for a moment, that the three-dimensional world you experience, the depth of the mountains, the solidity of your hand, the vast distances between stars is not fundamentally three-dimensional in its deepest essence. What if it is, in some profound and mysterious way, an illusion? A projection generated from information encoded on a distant, two-dimensional surface. This is the core, deeply captivating idea of the holographic principle and the holographic universe. To gently grasp this, let's think about a familiar technology, a hologram. When you look at a credit card or a security sticker, you might see a tiny flat image that, when tilted, appears three-dimensional, displaying depth and perspective. A hologram works by encoding three-dimensional information onto a two-dimensional surface using interference patterns of light. All the information needed to reconstruct the 3D image is subtly stored on that flat film. The holographic principle suggests that our entire universe might operate on a similar cosmic scale. It posits that all the information describing our seemingly three-dimensional universe, including time, might be encoded on a distant, two-dimensional boundary or surface. Perhaps at the edge of the observable cosmos, our perceived 3D reality, with all its stars, galaxies, and living beings, would then be a projection of this information. Much like the 3D image projected from a 2D hologram, this idea emerges from profound insights in theoretical physics, particularly from attempts to unify quantum mechanics with general relativity, especially when considering black holes. Stephen Hawking and Jacob Bekenstein made groundbreaking discoveries about black holes, finding that they possess entropy, a measure of disorder or information, and that this entropy is proportional not to their volume, but to the area of their event horizon, the two-dimensional surface from which nothing can escape. This was a radical departure from intuition. If black holes truly represent the most efficient way to store information, and if that information is stored on their surface area rather than their volume, it suggested that perhaps the universe as a whole might operate this way. It whispered that the information content of a region of space is not limited by its volume, but by its bounding surface. This led to the generalized holographic principle. The maximum amount of information that can be contained in a region of space is proportional to the area of its boundary. The most famous realization of this principle is the add-yes CFT correspondence, or Maldacena duality, proposed by Juan Maldacena. This highly technical concept suggests a profound mathematical equivalence between a theory of gravity in a certain type of curved spacetime anti-de Sitter space, or ADS, and a quantum field theory, conformal field theory, or CFT living on its lower dimensional boundary. Essentially, it's a mathematical dictionary that translates descriptions of gravity in higher dimensions to descriptions of quantum particles and forces in lower dimensions, and vice versa. While the ADS CFT correspondence describes a specific type of universe different from our own, our universe appears to be flat, not anti-de Sitter. It provides a concrete mathematical example of how a holographic principle could work. It suggests that a universe with gravity in a higher dimension can be completely described by a quantum theory without gravity. Living on a lower dimensional boundary, it's like saying a complicated 3D movie can be fully described by the 2D data on the film reel. If our universe is holographic, what does that mean for our everyday experience? It doesn't mean our reality is fake or that our experiences are unreal. Instead, it suggests a deeper, more fundamental layer of reality that is different from what we perceive. Our 3D world would be as real to us as the 3D image on a hologram is to an observer. It simply arises from information encoded elsewhere. Imagine the universe as an incredibly sophisticated cosmic projector. The projector itself is at the boundary, subtly encoding all the information about particles, forces, and interactions, and what we experience. The vastness of space, the flow of time, the warmth of a star, is the magnificent, vivid projection. It's a dance between information and manifestation. Where our perceived reality is the unfolding of encoded data, this concept subtly touches upon our discussions of the simulation hypothesis. If our universe is a hologram, it could be seen as a natural way for a higher dimensional reality to generate our lower dimensional experience. The program or code wouldn't be running on a traditional computer, but would be woven into the very fabric of the cosmic boundary itself, forming an intricate information structure that gives rise to everything we perceive. The holographic principle offers a potential pathway to reconcile gravity with quantum mechanics. In a holographic universe, gravity might not be a fundamental force in the traditional sense, but an emergent property that arises from the quantum interactions on the boundary. It would be a profound conceptual shift, offering a new lens through which to view the universe's most perplexing puzzles. However, proving the holographic principle for our actual universe is an immense challenge. Scientists are quietly looking for subtle blurs or fuzziness in spacetime at incredibly small scales, which might be a signature of this underlying holographic nature. Experiments, like those searching for quantum gravitational effects, are gently probing the very limits of our current understanding, hoping to find a whisper from the boundary. As we gently conclude this chapter, allow your mind to drift with these profound and elegant ideas about holographic reality. Ponder the possibility that the intricate, vibrant world you inhabit is a magnificent projection, generated from information encoded on a distant cosmic screen. Feel the quiet awe of a universe that is far more subtle and interconnected than our senses might initially suggest, where depth emerges from dimension and reality unfolds from information. There is a deep peace in this boundless mystery, in letting go of rigid definitions of what is real and embracing the universe's gentle capacity for infinite possibilities. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound and intricate layers. Take another soft, peaceful breath now, allowing the elegant idea of a holographic universe, where three-dimensional reality might be a projection from a two-dimensional boundary. To settle gently within your mind, we've journeyed through vast multiverses, the fluidity of space-time, the enigma of consciousness, and the potential for a simulated or projected reality. Today, we will softly turn our gaze to the ultimate fate of all things, a concept that stretches the very limits of our imagination, the end of the universe. Imagine, for a moment, that everything has a lifespan, from the shortest-lived quantum particle to the grandest galaxy, from the ephemeral flickers of consciousness to the vast, cosmic structures themselves. All things seem to follow a cycle of birth, life, and eventual decline. The universe, too, in its grand narrative, appears to have a story that began with the Big Bang, has unfolded over billions of years, and will inevitably reach a final chapter. But how that final chapter plays out is a profound mystery, a quiet whisper of different cosmic destinies. For many years, the primary determinant of the universe's ultimate fate was thought to be its density, how much matter and energy it contained. This led to three classic scenarios, each a gentle but distinct vision of the cosmos's demise. Firstly, imagine the Big Crunch. If the universe contained enough mass and energy, its collective gravity would eventually overcome the initial expansion from the Big Bang. The expansion would slow down, gently halt, and then begin to reverse. Galaxies would stop racing apart and instead begin to draw closer, accelerating their approach as gravity pulled everything inward. The universe would contract, growing hotter and denser, until all matter and energy compressed back into an incredibly hot, dense state, perhaps even collapsing back into a singularity. reversing the Big Bang. This is a poetic, cyclical end, suggesting that our universe's destruction might be the very seed of a new one, a cosmic inhale after a vast exhale. However, current observations, especially the accelerating expansion driven by dark energy, make the Big Crunch scenario seem increasingly unlikely. Secondly, imagine the Big Freeze, also known as heat death. This is the current favored scenario. Based on our observations of dark energy, if the universe continues to expand, and especially if this expansion continues to accelerate, galaxies will continue to rush away from each other at ever-increasing speeds, over unimaginable eons. The distances between galaxy clusters would become so vast that even light would take longer than the age of the universe to travel between them. Each galaxy, or even each star, would eventually become an isolated island in an ever-growing, empty void. Stars would exhaust their fuel, one by one, slowly dimming into cold. Dark remnants, white dwarfs, neutron stars, and black holes. These stellar corpses would eventually evaporate through Hawking radiation, a process so slow it takes longer than the universe's current age. Eventually, all matter and energy would be spread out so thinly that the universe would reach a state of maximum entropy, ultimate disorder, and uniformity. There would be no usable energy differences, no temperature gradients, no processes occurring. The universe would be infinitely cold, dark, and still, a state of eternal thermodynamic equilibrium. Time would, in essence, lose its meaning in a universe where nothing ever changes. It's a quiet, desolate end, not with a bang, but with an eternal whimper of ultimate stillness. Thirdly, imagine the Big Rip. This is a more dramatic, and perhaps more unsettling, possibility, one that arises if dark energy continues to strengthen over time. Rather than remaining constant in this scenario, the accelerating expansion would become so powerful that it would eventually overcome all forces that bind matter together. First, galaxy clusters would be torn apart. Then, individual galaxies would be ripped asunder. Stars and planets would be stripped from their orbits. Eventually, the very atoms themselves would be pulled apart. The fundamental forces unable to withstand the overwhelming expansive force of dark energy. Finally, space-time itself would be torn, unraveling into an ultimate, boundless nothingness. This is a violent, almost instantaneous end, where the fabric of reality itself is shredded, a sudden tearing of the cosmic tapestry. These three classical scenarios paint different destinies for our universe, each reflecting our understanding of the delicate balance between gravity and the forces driving expansion. But there are other, more subtle and even stranger possibilities gently whispered by theoretical physics. Consider the idea of a vacuum decay. We live in a universe with a very specific set of physical laws and fundamental constants, which collectively define the vacuum state of our universe. Think of it as a particular valley in the vast string theory landscape we discussed earlier. This vacuum is incredibly stable, but theoretical physics suggests that it might not be the most stable possible state. It could be a false vacuum, like a ball sitting in a shallow dip on a hill, rather than at the very bottom of the deepest valley. If this is true, then it's possible for our universe to suddenly and spontaneously tunnel to a lower, more stable vacuum state. This would be like the ball suddenly quantum tunneling through the hill to reach the deepest valley. When this happens, a bubble of true vacuum would spontaneously nucleate somewhere in our universe. This bubble would expand at nearly the speed of light. And inside it, the laws of physics would be entirely different. Our universe, as we know it, would simply cease to exist within this bubble, completely replaced by a new, utterly alien reality. It would be an end that comes without warning, a quiet, almost instantaneous transformation of reality itself. This scenario is highly speculative and unlikely, but it's a fascinating thought experiment, reminding us that the fundamental nature of our universe, its very laws, might not be as fixed and eternal as we perceive them to be. It's a universe that could fundamentally rewrite itself at any moment. A cosmic metamorphosis. Finally, let us consider an end that is less about destruction and more about a gentle fading or transformation into something utterly unknowable. If the multiverse is real, as we've quietly contemplated in previous chapters, then the end of our universe might not be the end of everything, but simply the end of our particular bubble of reality. Our universe might simply cease to inflate, or its specific configuration of curled-up dimensions might destabilize, causing it to merge with another, or simply fade into the background of an eternally inflating superspace. In this view, our end is merely a transition, a subtle rearrangement within a much grander, ongoing cosmic tapestry of realities. This offers a gentle reassurance that even if our universe meets its ultimate demise, existence itself, in its myriad forms, will continue in other branches, other bubbles, other mathematical structures. Our individual story may end, but the grand, boundless story of the multiverse continues its infinite unfolding. As we gently conclude this chapter, allow your mind to drift with these profound possibilities for the universe's end. Ponder the silent expanse of the Big Freeze, the dramatic tearing of the Big Rip, or the instantaneous transformation of a vacuum decay. Feel the quiet awe of existing in a cosmos whose ultimate fate is still a wondrous mystery, inviting endless contemplation. There is a deep peace in this boundless uncertainty, in letting go of the need for a fixed outcome, and simply embracing the universe's gentle, ever-unfolding story. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound and intricate narratives. Take another soft, peaceful breath now, allowing the contemplation of the universe's ultimate end, whether in a quiet freeze, a dramatic rip, or a subtle transformation, to settle gently within your mind. We've explored the grand scale of cosmic destinies, from the vastness of space and time to the potential for holographic realities. Today, we will softly turn our gaze to the most intimate and immediate aspect of our universe, something that underpins our very existence, the concept of the vacuum. Imagine, for a moment, what we typically understand as empty space. We often think of it as truly nothing, a void, a blank canvas upon which the universe paints its grand story. When all the stars, galaxies, and particles are removed, what remains for centuries? This concept of a true vacuum, a perfect absence of everything, was a foundational assumption in physics. It was the absolute zero of existence, a serene backdrop of pure nothingness. But the universe, in its gentle complexity, often delights in defying our simplest intuitions, just as we've seen space and time reveal their dynamic natures. The vacuum, too, holds secrets far stranger and more active than mere emptiness suggests. According to quantum mechanics, the vacuum is anything but empty. It is a vibrant, seething cauldron of activity, a dynamic sea of potential, even in the deepest, coldest reaches of space. This is the concept of the quantum vacuum. We briefly touched upon this when discussing the quantum foam in Chapter 8. But let us gently delve deeper now. The quantum vacuum is not a passive void. It is a field of quantum fluctuations. This means that even in the absence of any matter or energy that we can directly observe, fundamental quantum fields are constantly fluctuating, like ripples on an invisible pond. These fluctuations are governed by the Heisenberg uncertainty principle, which tells us that we cannot precisely know both the energy of a system and the exact time it possesses that energy. This fundamental uncertainty allows for tiny, fleeting violations of energy conservation, as long as these violations are incredibly brief. What does this mean for the vacuum? It means that pairs of virtual particles and their corresponding antiparticles can spontaneously pop into existence from the vacuum, exist for an unimaginably tiny fraction of a second, and then annihilate each other. Returning their borrowed energy to the vacuum from which they emerged, imagine the deepest, darkest corner of space, far from any star or galaxy. To our eyes, it would appear utterly empty, but at an unimaginably tiny scale, if we could peer into it, we would see a ceaseless, chaotic dance of virtual electrons and positrons, virtual photons, virtual quarks, all flickering into and out of existence like transient ghosts. This is the vacuum foam, a constant, energetic bubbling that underlies all of reality. It's as if reality itself is always whispering, always experimenting with creation at its most fundamental level. This activity of the quantum vacuum is not just a theoretical speculation. Its subtle effects are observed and measured. One striking example is the Lamb shift in atomic spectra. Electrons orbiting an atomic nucleus experience tiny shifts in their energy levels, shifts that cannot be explained by classical physics alone. These subtle shifts are attributed to the interactions of the electrons with the constantly fluctuating virtual particles in the quantum vacuum. The electron is not just orbiting the nucleus in empty space. It's constantly interacting with a dynamic, invisible sea of fleeting quantum entities. Another compelling piece of evidence is the Casimir effect, which we also briefly mentioned. Two uncharged, perfectly parallel metal plates placed very close together in a vacuum experience a tiny attractive force. This force arises because the plates restrict the types of virtual particles that can appear between them, creating an imbalance in the quantum vacuum pressure. More virtual particles can exist outside the plates than between them, subtly pushing them together. It's a gentle, almost imperceptible push from the nothingness itself, revealing its hidden power. These observations tell us something profound. The vacuum, far from being inert, is a dynamic reservoir of potential energy. It holds within it the raw ingredients for creation. And this brings us to one of the most remarkable and mind-bending ideas in modern cosmology, the possibility that the universe itself emerged from the quantum vacuum. In some theoretical models, the Big Bang wasn't an explosion in space, but an emergence of space and time from a highly energetic state of the quantum vacuum. Imagine a tiny quantum fluctuation, an instability in this bubbling sea of potential. Under certain conditions, this fluctuation could have been amplified, growing exponentially through a process like cosmic inflation, creating the vast, expanding universe we inhabit. Our entire cosmos, with all its galaxies, stars, and life, could be seen as a colossal quantum fluctuation that simply kept on growing, manifesting its potential from the initial nothingness. This idea offers a gentle, yet powerful answer to the question, where did everything come from? It suggests that everything came from nothing, not in the sense of absolute void, but from the incredibly fertile, energetic, and dynamic quantum vacuum, a realm of pure potentiality. It's a universe that is constantly giving birth to itself, endlessly unfolding its inherent possibilities. Furthermore, the concept of vacuum is crucial for understanding dark energy. As we explored, dark energy is the mysterious force accelerating the universe's expansion. One leading candidate for dark energy is the vacuum energy itself, an intrinsic energy density of empty space. If the quantum vacuum is indeed a seething sea of virtual particles, these particles and their fluctuations could contribute a tiny, but pervasive, repulsive pressure to the fabric of spacetime, causing it to expand at an accelerating rate. It's a subtle push from the emptiness itself, dictating the ultimate fate of the cosmos. This suggests that the vacuum is not just the stage, but also a key player in the universe's grand drama, influencing its birth, its evolution, and its ultimate destiny. It's a testament to the universe's elegant economy, where even nothing is filled with profound significance. As we gently conclude this chapter, Allow your mind to float with these profound and sometimes counterintuitive ideas about the vacuum. Imagine the silent, ceaseless bubbling of virtual particles even in the deepest void, a hidden ocean of fleeting possibilities. Feel the quiet awe of a universe that might have emerged from this very nothingness, and whose ultimate fate is subtly influenced by its intrinsic energy. There is a deep peace in this boundless potential, in letting go of rigid notions of emptiness and embracing the universe's gentle, dynamic nature. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound and intimate secrets. Take another soft, peaceful breath now, allowing the vibrant, dynamic nature of the quantum vacuum, a nothingness teeming with potential, to settle gently within your mind. We've explored how seemingly empty space is alive with fleeting particles and how it might even be the source of all existence. Today, we will softly turn our gaze to a concept that challenges our deepest understanding of what is real, suggesting that the universe might hold information in ways we are only beginning to comprehend. The idea of information as fundamental. Imagine, for a moment, that the universe, at its very core, isn't made of tiny particles or vibrating strings, but of information. What if every aspect of reality, every particle's spin, every photon's wavelength, every moment in time, every curve in space-time is ultimately a bit of information, a binary code, a series of yes-no answers that collectively describe everything that exists? This is the profound, almost mystical core of the idea that information is fundamental to reality, a concept often explored through the lens of it from bit. This phrase, it from bit, was coined by the brilliant physicist John Archibald Wheeler, a mentor to many great minds in physics, including Kip Thorne and Hugh Everett III. Wheeler, with his deep poetic intuition, wrestled with the mysteries of quantum mechanics and the universe's origins. He proposed that behind the apparent physical reality, there lies a more fundamental, informational substrate. In his view, every physical it, every particle, every field derives its existence and properties from intangible bits of information. To gently grasp this, let's reconsider some concepts we've already explored. Think of the black hole entropy we touched upon with the holographic principle. The fact that a black hole's information content is proportional to its surface area, not its volume, strongly hints that information might be stored in a way that transcends our usual three-dimensional understanding of space. A black hole, in this sense, isn't just a physical object, it's an ultimate information storage device. A cosmic library. Consider also the nature of quantum mechanics itself. When we observe a quantum particle, its blurred superposition of possibilities collapses into a definite state, revealing a specific piece of information. Its spin is up, not down. Before the observation, the information was ambiguous. After, it is definite. This process suggests that information is not merely a consequence of physical interactions, but might be intimately tied to the very act of defining reality. The universe, at its deepest level, seems to be processing and revealing information. The idea that information is fundamental also resonates with the simulation hypothesis. If our universe is a simulation, then its underlying reality is inherently computational, meaning it's built from bits of information. The physical properties we perceive are simply manifestations of this underlying code, much like the images and objects in a video game are rendered from digital data. In this view, information isn't just a description of reality, it is reality. But what kind of information are we talking about? It's not just the information stored in books or on computer hard drives, it's a more abstract, fundamental kind of information that defines the very properties and relationships of everything that exists. It's the information that distinguishes one particle from another. That dictates how forces interact. That determines the very fabric of spacetime. Some physicists and philosophers explore this through the concept of a pan-computationalism, which gently posits that the universe is, in some profound sense, a giant computer, constantly computing its own existence. This doesn't necessarily mean it has a CPU or RAM in the way we understand them. Rather, it means that the fundamental laws of physics are like algorithms, endlessly processing information and evolving the state of the universe from moment to moment. Every interaction, every change, every event is a form of computation. Imagine the universe as a vast, intricate network of interconnected yes or no questions, each answered by a fundamental bit of information. The collective answers to these questions weave together to form the rich, dynamic tapestry of reality that we experience. Our very existence, our thoughts, our perceptions are all part of this grand, cosmic computation. This view can be deeply empowering. If the universe is fundamentally information, and if our consciousness is capable of processing and creating information, then there is a profound connection between our minds and the cosmos. Our act of understanding, of discovering the laws of physics, is, in a sense, like reading the universe's own code, tapping into its fundamental informational structure. It also suggests a certain elegance and economy in the universe. If reality is information, then everything can be described with precision and without redundancy. It speaks to a universe that is maximally efficient, expressing its vast complexity through the most fundamental building blocks of data. However, like many of the profound ideas we've explored, the it from bit concept and the idea of information as fundamental are still highly speculative and challenging to test directly. How do you measure a bit of reality? How do you distinguish between information describing reality and information being reality? These are questions that continue to invite quiet contemplation and further scientific inquiry. Yet, this gentle whisper from the depths of theoretical physics offers a profound perspective. It suggests that perhaps the deepest truth about the universe isn't found in its visible matter, its energy, or even its space-time, but in the subtle, intangible patterns of information that underpin it all. It invites us to consider that reality is not just about stuff, but about relationships, about patterns, about meaning, all encoded in the silent language of cosmic data. As we gently conclude this chapter, allow your mind to float with these profound ideas about information as the universe's deepest secret. Ponder the possibility that every particle, every moment, every thought is ultimately a bit of cosmic data. Feel the quiet awe of a universe that is constantly computing its own existence, revealing itself piece by piece through the unfolding of information. There is a deep peace in this boundless abstraction, in letting go of rigid notions of physicality and embracing the universe's gentle, informational nature. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound and ethereal concepts. Take another soft, peaceful breath now, allowing the deeply abstract idea of information as the fundamental bedrock of reality to settle gently within your mind. We've explored how it from bit suggests a universe woven from cosmic data, continually computing its own existence. Today, we will softly turn our gaze to a concept that challenges the very notion of cause and effect, one that whispers of influences flowing backward in time, or perhaps existing beyond the linear progression we perceive. We will drift into the subtle and perplexing world of retrocausality and block universe theory. Imagine, for a moment, that the future, in some sense, already exists, not just as a set of possibilities, but as a definite, albeit unrevealed, reality. And what if events in this future could, in some subtle way, influence, or even determine events in the past. This is the core, deeply counterintuitive idea of retrocausality, where cause and effect are not strictly bound to flow only forward through time. In our everyday experience, cause always precedes effect. Dropping a glass causes it to shatter after it hits the floor. Firing an arrow causes it to hit a target after it leaves the bow. This linear progression of time, from past to present to future, with causes always preceding their effects, is so fundamental to our intuition that it's difficult to imagine anything else. This is often called the arrow of time, a relentless, unidirectional flow. However, the strange rules of quantum mechanics sometimes offer glimpses that challenge this intuitive arrow. Consider the famous phenomenon of quantum entanglement. Imagine two particles, perhaps two photons, that are entangled. This means their fates are inextricably linked. No matter how far apart they are, if you measure a property of one entangled photon, say, its spin, the other entangled photon, instantly and seemingly simultaneously, takes on the corresponding opposite spin, even if they are light years apart. This spooky action at a distance, as Einstein famously called it, implies an instantaneous connection that seems to defy the speed limit of light. But what if, instead of instantaneous communication, there's a subtle form of retrocausality at play? Some interpretations of quantum mechanics playfully suggest that the measurement of the first photon retroactively influences the state of the second photon in the past, before it was even measured, or that the future choice of which property to measure on the second photon might, in some subtle way, influence the state of the first photon at the moment they were created and entangled. This is a very speculative and debated interpretation, but it illustrates how quantum weirdness can gently push against our linear understanding of cause and effect. Another fascinating quantum experiment that whispers of retrocausality is the delayed choice quantum eraser experiment. This experiment is a mind-bending variation of the classic double-slit experiment, where light behaves as both a wave and a particle. In the delayed choice experiment, the choice of whether to observe the light as a wave or a particle is delayed until after the light has already passed through the slits. And yet, the light seems to know whether it will be observed as a wave or a particle. Exhibiting the appropriate behavior, it's as if the future decision subtly influences the past behavior of the light. This isn't a universally accepted interpretation, and there are many ways to explain such experiments without invoking retrocausality, but it remains a quiet, persistent puzzle. These quantum phenomena lead us to a deeper, more philosophical concept that profoundly challenges our perception of time, the block universe theory. Imagine, if you will, the universe not as a flowing river, but as a vast, immutable, four-dimensional block. In this block, all of space and all of time exist simultaneously and eternally. The past, the present, and the future are not distinct, fleeting moments that come into being and then vanish. Instead, they are all equally real, fixed points within this timeless block. Think of it like a loaf of bread. Each slice represents a moment in time, a present moment, but the entire loaf, with all its slices, exists simultaneously. You, as a conscious observer, are simply moving through these slices, experiencing them one after another, creating the illusion of a flowing now. But for the block universe itself, the entire loaf, from its beginning to its end, is already there, existing as a whole in the block universe. There is no true flow of time, and no such thing as a future that is yet to be determined. Every event, every choice, every consequence, from the Big Bang to the universe's ultimate end, is already set. An unchangeable part of this four-dimensional cosmic block. Your birth, your present moment, and every moment of your life yet to come are all fixed points in this vast, timeless structure. This concept arises naturally from Einstein's special and general relativity, In these theories, time is treated as a fourth dimension, on equal footing with the three spatial dimensions. If you can move freely through space forward, backward, left, right, up, down, why not through time? While we perceive a directed flow, the mathematical framework of relativity treats all moments of time as equally real and accessible within the space-time continuum. The block universe view has profound implications for our understanding of free will. If the future is already determined and eternally present within the block, does that mean our choices are merely illusions? Are we simply playing out a pre-written script? This is a deep philosophical question that continues to spark quiet debate. Some argue that free will can still exist within a block universe, perhaps as our conscious experience of making choices even if those choices are already there within the block. Others see it as a fundamental challenge to the very idea of agency. This view can be both unsettling and deeply calming. Unsettling, because it challenges our most basic intuition about novelty and the open future. Calming, because it implies a universe of perfect completeness, where nothing is lost and every moment, every experience, is eternally preserved within the cosmic block. The universe is a finished masterpiece, and we are simply unfolding our perception of it. If the block universe is real, then retrocausality might not be so strange after all. If all events in time are equally present, then the idea of an influence from one point in the block to another, regardless of their apparent temporal order, becomes less paradoxical. It's like tracing a line on a pre-drawn map. The line already exists, even if you are only just now drawing it. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes unsettling ideas about time's true nature. Ponder the possibility of a block universe, where past, present, and future are all eternally present. Consider the quiet whispers of retrocausality, challenging our linear notions of cause and effect. There is a deep peace in this boundless mystery, in letting go of rigid perceptions of time and embracing the universe's gentle, interconnected flow. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound and intricate narratives. Take another soft, peaceful breath now, allowing the mind-bending ideas of retrocausality and a timeless block universe to settle gently within your mind. We've explored concepts that challenge our linear perception of cause and effect and the very flow of time. Today, we will softly turn our gaze to something both intimately familiar and profoundly mysterious: gravity. Imagine, for a moment, that gravity isn't merely the force that pulls an apple to the ground or holds us to the earth. It is, in its deepest essence, the grand architect of the cosmos, shaping the universe on scales both infinitesimally small and unimaginably vast. It is the silent, pervasive force that orchestrates the dance of galaxies, sculpts stars, and even creates the most enigmatic objects in the universe. For centuries, our understanding of gravity was dominated by Isaac Newton's elegant description. He famously described gravity as a force, a mysterious, invisible pull between any two objects with mass. The more massive the objects, and the closer they were, the stronger the pull. This simple yet incredibly powerful law explained everything from falling apples to the orbits of planets, and it served humanity brilliantly for over 200 years. It was a comforting, predictable universe governed by clear, universal laws. But the universe, in its gentle complexity, often hints at deeper truths. Newton's gravity worked wonderfully for most everyday phenomena, but it struggled to explain certain subtle observations, like the precise orbit of Mercury around the Sun. And, more fundamentally, it didn't explain how this force acted instantaneously across vast distances, a concept that even Newton himself found perplexing. Then came Albert Einstein, And with his general theory of relativity in 1915, he profoundly revolutionized our understanding of gravity. He didn't just describe gravity, he fundamentally reimagined it. For Einstein, gravity is not a force but a manifestation of the curvature of spacetime. Imagine spacetime, as we discussed in Chapter 8, as a vast, flexible, four-dimensional fabric. When a massive object, like a star or a planet, is placed on this fabric, it creates a dent or a warp in the fabric. This curvature is what we perceive as gravity. Objects, like planets orbiting a star, are not being pulled by a mysterious force. Instead, they are simply following the straightest possible paths through the curved geometry of spacetime caused by the presence of the massive object. It's like rolling a marble across a stretched rubber sheet that has a bowling ball resting on it. The marble's path curves not because the bowling ball pulls it, but because the sheet itself is distorted. This idea is incredibly elegant and powerful. It explained the anomalous orbit of Mercury perfectly and made stunning predictions that were later confirmed, such as the bending of light by gravity. Einstein predicted that light, even though it has no mass, would have its path curved as it passed near a massive object, because spacetime itself is curved. This was famously confirmed during a solar eclipse in 1919 when Arthur Eddington observed starlight bending around the sun. It was a quiet, profound validation of Einstein's radical new vision. This means that gravity is not just a force, it's a property of the universe's very geometry. It's woven into the fabric of reality itself. Every object with mass and energy contributes to the curvature of space-time around it. And in turn, this curvature dictates how all other objects move. It's a continuous, silent conversation between matter and the cosmic stage upon which it dances. But gravity holds even more dramatic secrets when matter is incredibly dense, or when it collapses under its own immense gravity. It can create regions of extreme space-time curvature that lead to the formation of black holes. A black hole is a point where space-time is so profoundly curved that nothing, not even light, can escape once it crosses a certain boundary called the event horizon. Inside a black hole, our current understanding of physics breaks down, suggesting that gravity reaches an infinite density at a point called a singularity. Black holes are cosmic leviathans, powerful engines that shape galaxies and hint at the ultimate mysteries of gravity. Gravity also played a pivotal role in the Big Bang. It was the initial force that caused matter to clump together after the universe's fiery birth, forming the first stars and galaxies from the subtle density fluctuations in the early cosmos. And it continues to be the dominant force on the largest scales, orchestrating the cosmic web of galaxies and galaxy clusters, drawing them together into vast, intricate structures. However, despite its immense success in describing the universe on large scales, gravity remains a profound puzzle when we try to understand it at the very smallest. Quantum scales. General relativity. Einstein's theory of gravity is a classical theory. It describes gravity as smooth, continuous curves in spacetime, but quantum mechanics, which describes the other three fundamental forces: electromagnetism, strong nuclear force, weak nuclear force, and the behavior of particles, is inherently discrete and probabilistic. These two pillars of modern physics, which have been incredibly successful in their respective domains, famously do not get along. When physicists try to combine gravity with quantum mechanics to create a theory of quantum gravity, the mathematics often breaks down, yielding infinite and meaningless results. This is the quest for a theory of everything, a single, unified framework that can describe all fundamental forces and particles, including gravity, at all scales. This challenge has led to many speculative, yet elegant, ideas. String theory, as we explored in Chapter 11, is one of the leading candidates. In string theory, gravity is not a separate force, but just another vibration of a tiny, fundamental string, represented by a particle called the graviton. Because strings are not point-like, their interactions are smeared out over a tiny region. which helps to avoid the mathematical infinities that plague other attempts at quantum gravity. Another approach is loop quantum gravity, which attempts to quantize space-time itself, suggesting that space is not continuous but made of discrete, indivisible loops or atoms of space-time. Like tiny pixels in this view, gravity would emerge from the intricate arrangement of these quantum loops, a fundamental granularity to the cosmic fabric. The quest for quantum gravity is a quiet, persistent whisper in the halls of theoretical physics. Driven by the profound desire to understand gravity's true nature at its deepest level, it's a journey into the very fabric of reality, seeking to understand the quantum nature of space-time itself. As we gently conclude this chapter, allow your mind to drift with these profound ideas about gravity. Ponder its silent role as the architect of galaxies, the sculptor of stars, and the creator of black holes. Feel the quiet awe of a universe where gravity is not just a force, but a dynamic curvature of space-time itself, a continuous dance between matter and the cosmic fabric. There is a deep peace in this boundless mystery, in letting go of simple definitions and embracing the universe's gentle, intricate nature. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence.